Cool. Thanks for Winshuo's introduction. And today we will have several speakers to introduce your research. And we will have Professor Cassie Wu from MIT, Professor Dustin Markula from University of Leeds, and Professor Igor Gildashinsky from University of Toronto, and Yan Chang from Zoox, and Dr. Yixiao Chen from NVIDIA, and Mr. Olger Zibinga from Delft University of Technology, and Professor Catherine Driggs-Campbell from UIUC. And now let's welcome our first speaker, Cassie Wu. And Professor Cassie Wu is an assistant professor at MIT in IDS, CEE, and IDSS. She holds a PhD from University of California at Berkeley and Bachelor and Master of Engineering from MIT, all in WCS, and completed a postdoc at Microsoft Research. Her research interests are in the intersection of machine learning, decision-making, and mobility. Her current work focuses on how learning-based methods can advance emerging mobility systems by better coping with the complexity of decisions and control. She is broadly interested in enabling policy-relevant research by pushing the boundaries of learning, control, and optimization. Cassie has received a number of awards, including the NSF Career Dedication Awards and publications with distinctions. Her work has appeared in the press, including Nova, Weird, Science Magazine, the MIT homepage, and Catalyst. Now let's welcome our first speaker, Professor Cassie Wu.
Thanks so much. It's my honor to open up this first workshop on socially interactive autonomous mobility. And I apologize that I couldn't be there with all of you today, but I do welcome interaction. So if you have any questions in the middle, please feel free to interrupt, and hopefully the moderators can direct the questions. So I would say that the socially interactive portion is something that is implicit in the work, but yet there is a lot of room to grow. So I loved the triangle that you guys had in terms of bridging these communities together. So I also look forward to learning a lot from you all. What I'm going to talk about today has to do with, to some extent, stepping back from where we have been in terms of thinking about autonomous vehicles and what they can do to our mobility systems. So I'll be sharing some of our recent work on intelligent coordination for sustainable roadways, and sort of somewhat provocatively thinking about the question of, if autonomous vehicles are the answer, then what actually is the question? Before I jump into things, I like to just open with what gets me up in the morning, which is questions roughly in this space. It's work that has the potential to leverage emerging technology to improve people's lives while working on interesting technical questions. And this coincides pretty well to the research communities that I interact with. This is like a slightly different triangle. And these are the autonomy community, the intelligent transportation community, as well as the learning for decision and control community. Okay, now this is preaching to the choir to all of you in this room. But because it's so easy to take for granted something that we use and rely on every day, I like to just start by saying that roadways are the circulatory system of the economy. They link producers to markets, workers to jobs, students to schools, and sick to hospitals, among other functions. At the same time, they are not perfect. They are far from it. And one of the approaches that we have been working on for the last roughly 20 years to substantially improve roadways has been autonomy. So the way this goes, the rationale is, for lack of a better term, let's call this autonomy-driven design. The idea is, if we can achieve autonomy, then vast societal benefits will be unlocked. So it goes something like this. Let's figure out perception, planning, compensates, reasoning, social orientation, altruism, many of the topics we're going to discuss today in terms of the social factors. And if we figure these parts out, then we will be able to achieve more sustainable roadways in terms of safer, cheaper, cleaner mobility. So as evidenced by this not having happened yet, despite this being probably one of our major approaches over the last several decades is we can say this has been harder than we thought. So I have a lot more to say about this, but I want to be brief in this so that we can focus more on the technical work. But essentially what I'm going to do in this talk is I'm going to try to give some examples or one example of how we might make forward progress by taking a bit of a different approach. So rather than this rationale that goes left to right, we're going to take basically this different approach which goes from right to left. So we're going to start with the idea that what we want is to achieve sustainable roadways. And we're going to ask the question of what do we need to actually move the needle? So also for lack of a better term, let's call this use-driven design rather than autonomy-driven design. And essentially what we're going to ask is, for this original approach, is autonomy necessary or only sufficient? Okay, and we'll give some greater examples. And the opportunity is that perhaps we don't need every aspect of what we need to build autonomy in order to achieve the right-hand side of more sustainable roadways. Okay, so to put this in context of the title of the talk, sorry, the slide is slightly messy. I want to take a step back because where we are in terms of autonomy is it's not out there. We don't know how to launch it. We don't know what it's for, and we don't know how to achieve what we want it to achieve. So that leads to this question of what if autonomous vehicles are the answer, what is the question? So let's break this question into several pieces, which are highlighted in red. So what do we actually want to achieve with autonomy? I'm going to give one example that I've been working on, which is eco-driving, which we'll talk a little bit more about. And the second question is, at what cost? At what cost are we willing to, and at what cost would it take to achieve what we want to with autonomy? And then the third question is, how do we systematically answer these questions? I hope that I can convince you in this talk that one answer to this question, which is what is the question, is how can intelligent coordination achieve more sustainable roadways? Okay, so let's jump into the first part, which is going to be sort of what do we want to achieve with autonomy? So for this, we're going to talk about eco-driving for the planet using multitask learning. This is done in collaboration with many of my students, and it's still an ongoing project. It's probably the largest project I've ever undertaken. It has several, it's sort of broken down into two components, modeling and control. And here are sort of the sample preliminary publications that I'll mention here. So the main motivation of this work is that we urgently need to decarbonize transportation. And transportation is the largest contributing sector of greenhouse gas emissions in the US at around 29%. A vast majority of these, around 80%, are actually on roadways. Electrification is good. It is not the only answer. Autonomy could enable all sorts of efficient uses of vehicles, which includes accelerating electrification, sharing of vehicles, platooning, vehicle right sizing, and so on and so forth. We're going to focus on one specific opportunity, which has to do with how traffic signals induce stop and go basically everywhere and all the time. So here is a video of an intersection. This is just sort of for illustrative purposes. You can see that there are vehicles and they sort of queue during the red and green phases of the traffic signal. What has really informed this research is this back of the envelope calculation. So about half of vehicle miles traveled actually are close to signalized intersections. And there's a lot of research on what's called eco-driving that attempt to quantify the avoidable emissions around signalized intersections. And a very coarse meta-analysis, I just literally took all the studies reported in this survey and took the plus minus 1 standard deviation of the reported values, and I get something like 6 to 28% of the emissions could actually be avoidable. If we're optimistic and we take this upper range, we see that up to 15% of CO2 from driving could simply be wasted at intersections. This is emissions that is not really doing anything for us. It's just wasted. It doesn't improve our quality of life to emit. So also for illustrative purposes, here on the right-hand side, this video illustrates what if we were to give some guidance to vehicles, in this case, all vehicles, as they approach the intersection. So this is known as eco-driving. And how much emissions could this mitigate? So this is the back of the envelope calculation. This is not enough to say, okay, let's go to Congress and put in a bill to do this, because this is a wide range. It's not really clear if this maps to. It's not really clear what was studied in these particular studies. Why is there such a large range, and so on. So this leads me to our research question, which is, would coordinating vehicles to reduce the CO2 emissions at intersections actually move the needle on climate change mitigation goals? There is a vast literature on this topic known as eco-driving at signalized intersections. There are some at least 50 supportive studies that sort of indicate this is reasonably a good idea. But a curiosity is that we don't really see any mass deployments. And one curiosity is sort of why. Our goal here is to, rather than investigate how to eco-drive, which has been the focus of these 50 studies, but rather ask the question of should we? Okay, so contextualizing eco-driving with respect to national priorities such as climate change mitigation. So what we essentially want to do in this work is we want to estimate the expected improvement of eco-driving over the possible driving scenarios. Okay. So the central challenge of this work has to do with the diversity of intersection scenarios. To illustrate this, consider Salt Lake City, which is our partner in this work with the Utah Department of Transportation. So here's a picture of one intersection. An intersection has several attributes. For instance, the number of approaches, the number of lanes in each approach, the turning restrictions. If we look at different intersections, we see different attributes, different values for these attributes, which indicates that we have just looking at the topology of the intersection, we see different configurations, different scenarios. Different scenarios induce different control problems when it comes to eco-driving. And these are only the factors that are easy to visualize. There's also road grade, the weather, the travel demand, the vehicle types and age, and so on. Okay, so this diversity of intersection scenarios essentially induces a lot of different control problems that we need to analyze in order to answer this question of what is the expected value of the eco-driving effectiveness. So let me now be more explicit about the challenges. One, eco-driving controller design in the past has really focused on specific settings. So there is no known approach that can simultaneously handle all the considerations that we need to here, which include global objectives, lateral dynamics, road grade, et cetera, et cetera. We also don't handle everything here, but we're stepping towards that direction, I should say. Suffice to say that there is no known approach that scales to analyzing millions of scenarios. So we take a multitask deep reinforcement learning approach for this problem. The second challenge is quite unfortunate because this is not really the strength of researchers. The second challenge is that large-scale modeling of traffic has really focused on highways, whereas here, in order to answer this question, we really need large-scale modeling of urban settings as well as other eco-driving factors. So we also need to tackle this as well. So, okay, we need to do the modeling before we can do the control. So let's jump into that. Okay, so for large-scale modeling, the only conceivable way that we thought of at first to do large-scale modeling is to pull down data from OpenStreetMaps. This allows us to quickly acquire static factors such as the lane length, speed limits, et cetera, for large metropolitan areas. And we selected these based on large emitting regions as well as our partner in Salt Lake City. Unfortunately, if any of you have worked with OpenStreetMaps, you know how wonderful it is. You also know how terrible it is. It is, many of the attributes are missing. So something like 95% of the attributes are missing, 95% of the lane length, speed limits, et cetera. So we devised an imputation methodology, which we presented earlier this year at TRB, to actually impute the missing quantities It is not perfect, it's far from perfect, but it is better than not having any attributes, I should say. So this allows us to impute the static factors, which gives us that diversity of scenario for major metropolitan areas in the US. This is not enough. These are only static factors, but with eco-driving, we also need to have a sense of the dynamics of the intersection environments. So for this, we have additional non-static factors that we need to model, such as the seasonality, the driving demand during peak and off-peak hours, weather conditions, as well as for our analysis purposes, what percentage of vehicles are we guiding, okay, in terms of doing eco-driving. So overall, this leads us to over 1 million scenarios. So this presents a large challenge for previous approaches on eco-driving. We also have to sort of put this all together in terms of how do these factors ultimately become an environment and lead to the eco-driving metric in the end. I don't want to belabor this, but it's a big complicated exercise. And I'll just show that the static factors are a small piece. There are many, many more factors, which include the sort of non-static factors. I will highlight one piece of our work in this direction that actually, I would say without this, we would not have been able to move further in this work, is that there's an industry standard emission model known as the EPA MOVES model, which actually already captures a lot of the factors that we need. It's an amazing model. You can input the vehicle age, the vehicle type, the humidity level, the temperature, and it will give you the emissions of that vehicle. It's an amazing program. Unfortunately, it's not designed for a very large scale application. So our back of the envelope calculation said that we would need something like 9 compute years to analyze the 1 million plus scenarios. So our solution as sort of machine learning people is to see what we can do to learn surrogate models to actually accelerate this emission model. So the rationale goes, okay, we have this emission model, moves, and it underlying it is probably these continuous functions, because emission models are these smooth continuous curves. It's physics after all. But it can also take in various attributes such as the age of the vehicle, the humidity, and all that, and other attributes. And so, can we extract this data and fit functions to this? And we're finding we found success in doing so. So this actually allows us to take this large program, which is amazing, but not very, very fast. It's a sort of large Java program, requires a Windows environment and so on. And it allows us to distill it into a small neural network. Okay, so with that, we're able to do, I think, a considerable degree of the modeling piece. And so now let's move on to the control piece. For the sake of tractability, we're going to focus on just the acceleration of the vehicles. I would say the vehicles do lane change, just not in a learned manner, and as do the surrounding vehicles. So with that, we can now talk about the multitask methodology. So the general idea behind multitask is that we try to learn, for instance, a single controller for a variety of environments. Here, an environment is all of the scenarios that we have modeled in the past few slides. So here we can see that we'll sample some scenario, we'll collect data from it using the current iterate of the policy, and we will do this over and over again to collect several rollouts from several different environments. We will update the policy accordingly. The policy will sort of take in the classical observations, which includes what vehicles can see and what they can sense from or communicate with the infrastructure. But it will also include a context vector, which distinguishes between different environments, such as the humidity level and the vehicle type and so on and so forth. Okay, so to summarize, a vehicle scenario variation is a task in the multitask lingo. Most of our training methodology, other than that, is pretty standard in terms of standard algorithms, architecture, training protocols. for a multi-agent setting because we're controlling multiple vehicles. One non-standard thing, which I won't belabor due to time, is the reward function. It is fairly non-trivial to design a reward function. We've had to do additional studies specifically for that. Okay, so this works okay, but what makes this work even better is a very small extension, which we call multitask reinforcement learning. So if you think about it, multitask reinforcement learning would learn a single policy for the million scenarios. And it's sort of reasonable to think that one policy will not do very well over all of these scenarios. And so what multitask reinforcement learning does is we do multitask reinforcement learning over a partition of the task space. This partition is determined heuristically, and there could be future work that does this in a more systematic manner. I will say our studies, they take several weeks to train each time, so we're not really being very systematic about this. We're really using domain knowledge regarding what is the best way to partition the space. In the end, we end up with something like 7 policies, which is not very large. It's still much less than the overall set of scenarios. And then to assemble the final set of control laws, we simply take the best control law for each scenario, not necessarily the one that it was trained for. Okay. So now let me just jump into the results. Again, this project is ongoing and the results are preliminary. So I'm going to give you the results for Salt Lake City, and we're sort of analyzing the remaining cities as well as digging deeper into the results. But what I can say is that at around 100% adoption, this yields about 11% reduction in fuel consumption. If we do a linear scaling from this to all intersections in the city, which makes distributional assumptions, this scales to about 1.5% reduction in overall US CO2. Is this good? Is this not good? One reference point that I have is that the venture fund led by Bill Gates, which is known as Breakthrough Energy Ventures, the gold standard for this venture fund is around 1% reduction in global greenhouse gas emissions. Interventions that have the potential to achieve this. Okay, so based on this, I would say that eco-driving is actually within this ballpark. Something else that we analyze is not just the 100% case, but also the partial adoption case. So at 20% adoption, we see about 28% of the benefit. Okay, so there's some nonlinear scaling. The benefit there is somewhat intuitive. So if there's a vehicle that's eco-driving, a vehicle behind it may benefit even if it is not eco-driving. Okay, so in summary, eco-driving at signalized intersections could substantially contribute to transportation decarbonization. We have done extensive modeling of urban traffic for 10 major US cities to fill a gap in traffic models beyond highways. And we also developed these neural surrogate models for the industry standard emission model, which is known as EPA MOVES, to accelerate and broaden access to diverse emission models. And finally, the multitask reinforcement learning allows us to actually analyze the over 1 million eco-driving scenarios. Okay, so that is the first piece. And hopefully what I aim to do in this talk is to give you a sense of how one may answer that question of, if autonomous vehicles are the answer, what is the question? And so I hope that this gives one possible answer, which has to do with improving the sustainability of our roadways. The second question is, yes, maybe we can achieve some good benefit that is even important within the context of our national priorities, but at what cost? Okay, because everything has a cost. So this leads me to the second part, which is about learning coarse grain driving policies. This is work also done in collaboration with my students, as well as my collaborator, Roy Dog at UIUC. This work has two aspects. There's average case analysis as well as worst case analysis. I'm going to focus here on the average case analysis. So when we talk about cost, I'm going to talk about the opposite. I'm going to talk about something that's very cheap. So we can roughly think of autonomous vehicles as like a way to coordinate cars, okay? A very cheap way to coordinate cars is to simply give drivers an app. You can sort of question like, is this autonomy, is this not? But if we put this in the spectrum of the levels of autonomy, ranging from level 0, which is a fully manually driven car, to level 5, a fully autonomous car, we could put this as something like a level 0.5. So we don't actually need the car to have any autonomy capabilities. This could be thought of as a very low cost, near-term form of autonomy. So what we know from research from like the first part of the talk, as well as our prior work, as well as many folks that are doing work in this area, we know that level 5 autonomous vehicles can boost system performance, even with a small fraction of vehicles. So they can boost performance on highways, urban settings, various scenarios. The question in this part of the talk is what this previous work shows is that it is sufficient to have a small fraction of level 5 cars. The question is whether it is also necessary, okay? So to systematically answer this question, you could say, okay, well, let's model level 4 cars, level 3 cars, level 2 cars, level 1 cars, level 0.5 cars. So because level 0.5 is so cheap, that makes it very compelling. So we just go all the way to that end and model that end. If it's not sufficient, we can always, increase the technical requirements. Okay, so we're going to start with a very simple model to answer this question of to what extent can guided human drivers achieve the traffic optimizing behavior of autonomous vehicles? Okay, similarly to the first part of the talk, as well as for the previous slide. You can think of the guidance as something simple that a human driver could conceivably satisfy. So for instance, something like a personalized dynamic speed limit or a personalized dynamic acceleration limit, okay? So we're gonna consider both of these. We're gonna consider a very simple model for the human. We're gonna say, okay, human drivers, autonomous vehicles can follow instructions very quickly. Like you can change the instruction very fast. With human drivers, they can't do that. You have to change the instruction very slowly. So we're going to model this using coarse grain control, coarse grain driving. So think of a piecewise constant guidance. So we're going to hold an instruction, a guidance for some period of time before changing it. And we're going to consider a range ranging from roughly 0.1 seconds, which is going to be modeling our autonomous vehicle, to something like 40 seconds. I don't know where the human is, it's somewhere in the middle, okay? So we'll just consider the range. This is also known as zero order hold in the control literature. So what we want to do is we want to design the coarse grain control laws, this pi sub delta, delta being the hold length. And the research question is how coarse of a guidance delta can still achieve the traffic optimizing behavior. Okay, so there's a simple model for the human driver. So the problem setup is that we're going to consider traffic scenarios such as the ones pictured here, where a fraction of vehicles rho are guided and a fraction 1 minus rho are unguided. Okay, so keep in mind now all vehicles are human driven. And the key difference is that the guided vehicles are going to follow this zero order hold policy, whereas the unguided drivers are going to follow a conventional driving model. Now, keep in mind that each combination of a guidance type, hold length, and traffic scenario yields a different traffic scenario. So we have this sort of diversity challenge again. Okay, but we can use learning for this. So we're going to that's exactly what we're going to do. We're gonna learn, and in simple scenarios, we're going to analyze the outcome. And just can I get a time check while I continue?
It's 9:03. It's like 12 minutes late.
Sorry?
It's like 12 minutes left.
Okay, thank you so much. Okay, so I'll jump right to the results and then talk a little bit about the methods. So for this model highway this we can think of as like the simplest traffic scenario we consider. And it's instructive for a few reasons. So first of all, a bit on the theory side is that the coarse-grained guidance coincides exactly with what's known as sample data systems in the control literature. This actually allows us to use a extension of Lyapunov analysis, known as Lyapunov-Krasovsky functionals, to derive sufficient conditions for system stability. What this allows us to do is just to build some intuition for ourselves that coarse-grained guidance does not cause the system to break immediately, okay? So that's sort of for the worst case analysis. For the average case analysis, which is what we're focusing on, we actually have some troubling signs. So take a look at this figure. So on the x-axis is the guidance length. So ranging from that 0.1 seconds to the 40 seconds. And these 0.1 seconds is going to model our autonomous vehicle, and the y-axis is going to be our system performance. We expect the system performance to degrade over time, but the reason to look at this model highway is that it is very nice. We know that there is an optimal velocity, okay? So if we just give the system that optimal velocity, we should be able to hold the optimal time for in an indefinite period, okay? So what we should expect in this is just a straight line. So we do see a straight line when we issue some speed guidance, but when we issue acceleration guidance, the trading actually gives some signs of brittleness. Okay, so this is actually somewhat troubling because the difference between this control problem and this control problem and this control problem and this control problem is essentially just the hold length. The underlying environment is the same, okay? But reinforcement learning is able to solve this one, but not this one, and not this one, and not this one. Okay, so that's a hint of brittleness, which we're going to come back to more generally later. For now, this motivates development of a method specifically for this problem, where we're actually going to leverage that. Actually, all these problems are essentially the same, okay? So this is what we call a temporal transfer method. So the key idea is to say, consider a particular hold length, and we're going to leverage two things. One is that coarser problems, so problems to the right, are essentially easier to solve from a decision standpoint because the effective horizon of the problem is shorter. Okay, so there are fewer decisions to get right in order to solve the problem. However, problems to the left could achieve a higher performance because the control is finer grain. Okay, so the algorithm, the key idea is to find a sweet spot where the performance does not degrade, but is easier to solve. And the challenge is that we don't know where these curves are prior to training and whatnot. Okay, so we basically propose a form of a stochastic binary search to identify the ideal source task that if we train successfully, we can sort of transfer to the target task. So using this idea, we're then able to apply this to the actual original problem. So going from this jagged red curve to this solid red curve, as well as more sophisticated settings. So here is this highway ramp setting where we have the vanilla training, which is this red curve that's very jagged, and then applying our method, the performance is much smoother. Okay. So from this, what we can also see is that there is performance degradation like we expect, but up to a large range of what we expect to be, in some sense, human compatible. We do preserve considerable benefits of the autonomy in the system. Okay, so in summary, the coarse grain control preserves the benefits from AVs across a variety of different traffic scenarios. And the key implication is that these guided human drivers could enable near-term, low-cost autonomy benefits. That vanilla deep reinforcement learning is unfortunately brittle to even very small changes in the environment, such as the action duration, but that this temporal transfer learning method can improve the reliability of learning these coarse-grained control laws. So I know I don't have too much time, but I would like to just touch base a little bit on now where do we go from here? What I hope I've conveyed so far is some ideas of how to answer that question of if autonomous vehicles are the answer, what is the question? Okay, so that has to do with how can we quantify the benefits of autonomy in a way that contextualizes it with the stakeholders of the system, and is it cost effective enough for those stakeholders? Both of those questions lead to solving a ton of control problems. Okay, and what we've seen is that these control problems sometimes are not able to be solved using off-the-shelf methods, and they require method development. That is somewhat troubling because we don't want to need to go back to the drawing board every time we want to answer one of these questions to design a new method. So we took a step back and are starting to try to answer this question of how do we more systematically answer these questions, as in be able to answer these new control problems, these vast ranges of different control problems. Like they're related to one another, but they're somewhat different. So this leads us to some work that we're doing on hybrid learning methods for multi-vehicle coordination. And here, this is joint work with my students. And I'm going to motivate this first by returning to the example that we just saw around brittleness of vanilla deep reinforcement learning for this coarse-grained control problem, where we're just changing the hold length, but the underlying scenario is the same. And we see drastic differences in the training performance with vanilla reinforcement learning. So we went back, we took a step back and thought, is it us? Is it the problem? Is it deep reinforcement learning? And for better or worse, we found similar brittleness in existing deep reinforcement learning benchmarks. So first, staying close to home, this is the RESCO benchmark. It is for traffic signal control, so controlling traffic signals, not cars, but it is still about intersections, okay? So what we did was we took the methods that were exposed in this benchmark, which include a variety of learning methods as well as classical methods, control methods, and we actually used some of the modeling we had done with Salt Lake City, which provides a variety of intersection environments. And what we did was we took those methods and we retrained them one at a time on each different environment here. And we tried to understand, is this brittle? Are these methods brittle? So what we found is that in the reported benchmark of RESCO, the learning methods, which are in red, some of them do outperform the classical and most commonly sort of referenced method, which is fixed time control. However, when we reevaluated the methods, as in retrained, what we see is that fixed time control actually comes out on top, okay? That actually implies that fixed time control is the least brittle among these methods. So this is rather unfortunate. We also went to the different standard benchmarks, and we found similar conclusions, though not as dramatic, because here we're mostly comparing learning methods with other learning methods. So what we are doing, I think I'll sort of skip this for the in the interest of time, but we are basically sort of now trying to think more systematically about where do we go from here, because these I think the hope was that pure learning methods, these deep reinforcement learning methods, would be able to solve these control problems and generalize to additional ones. But it is evidently not the case, even if you just change the environment a little bit. And so we're looking at these hybrid methods now, which have elements of learning, have elements of modeling. And we're looking at this first in the context of discrete optimization, because discrete optimization provides actually benchmarks, so to say, of variations of these control problems. So we've done this work for vehicle routing problems, where we have divided some techniques that can leverage something that we know about vehicle routing problems, which is that, you know, big problems, we can often decompose them into little problems, and people have found that to be a good idea. And we're incorporating learning in as elements into this in order to improve even the effectiveness of that. And so overall, I'm going to skip over, unfortunately, the details of this, but this sort of learning augmented, learning guided large neighborhood search, we're able to speed up sort of classical large neighborhood search by about 100%. And we're able to apply that same algorithm to variations of the vehicle routing problem and still achieve similar gains in performance. Okay, so overall, I hope that the main message of the talk is that autonomy may be sufficient, but not necessary for us to make substantial progress on sustainable roadways. This idea of use-driven design, again, for lack of a better term, is that we should really consider why we want to improve roadways, and then we should actually deliberately and systematically answer that question. And there are many algorithmic challenges along the way that we also need to consider. And with that, thank you all for your time, and I'm happy to take questions.
Thank you, Professor Cassie. That's a perfect presentation. Now, any questions from the audience?
Hi, Professor Wu. Can you hear me?
Yeah.
Thanks for your amazing presentation. I have one question about the first part. So you mentioned you use some topology information of the traffic scenarios. I mean the signalized intersections for your model. So could you provide a little bit more information about what kind of topology information in your model?
Yeah. So the topology information that we use is listed here in the static factors. So we model the length of the lanes, the number of lanes, the slope of the road or the road grade, the speed limits, and the turn lane configurations, as in turning restrictions.
Okay. So in your result, do you find some conclusions like what kind of influences of these static factors on your model performance?
Yeah, we have done that analysis. I don't have the plot with me right now. There are some factors that don't seem to have much relation. Okay. Don't quote me, but I think like lane length is a very important, I think lane length is very important. I think the demand is quite important. And yeah, we're still doing the analysis, like sort of city by city.
Okay, yeah. Because previously I have some work to do analysis on the signalized intersections. So I encountered one problem is how to do classification of the scenarios. I noticed that you mentioned you do analysis on about 0.8 million scenarios. So here the scenarios means different intersections, or what's the scenarios here specifically?
Yeah, so the scenarios here is we try to spell it out mathematically here. So we have the each physical scenario right here, like the that is a combination of the static factors, and then multiplied by the seasons, multiplied by the peak and off peak, multiplied by the penetration level condition.
Okay, so how about the information about the traffic light control? For example, for some signalized intersection, we have the left turn signal, but some not. So do you add some information about the
yes, control? I think yes, we do have that. So this is not exhaustive in terms of so this was actually meant to convey the number of scenarios. We do have this is what I didn't talk about. So we do have the sort of signal plans. We do so we take the plans, like the number of phases and the types of phases, but we actually we are only considering we're sort of assuming fixed time plans in our work, because we don't have access to the timing information for at a scalable level. Yeah, so there's sort of more modeling in this, but it doesn't contribute to more scenarios, if that makes sense.
Okay.
It's sort of one per intersection. Yeah.
Okay. Thanks for your answers. Yeah.
Yeah. Thank you.
Any
Gustav.
questions?
I think Gustav has a question here.
Yeah, if I have time, I think you maybe sort of answered it just now. Thanks for a really nice talk. So do I understand correctly that you're still assuming in this example here that the traffic lights are still there, they're working as usual? The only thing you're optimizing is just like the speed control of the vehicles in relation.
Yeah, that's right. So integrating into the existing system.
Cool, really nice. Thanks.
That's cool. And if you have any further questions, please feel free to directly contact Professor Cassie Wu. And let's thank Professor Cassie Wu again.
Thank you all.
And let's welcome our next speaker.
Yeah, it's my pleasure to welcome Professor Gustav Makula. He happened to examine my PhD thesis. So Professor Gustav Makula is an engineer by training and applies quantitative methods and models to the study of human behavior and cognition in road traffic. He has a background in automotive industry research and development, particularly at Volvo, and is currently the chair in applied behavior and modeling at the Institute for Transport Studies, University of Leeds, in the United Kingdom. In his research, he specializes in the adoption and integration of models from computational cognitive neuroscience to support development and testing of safe and human acceptable technology and automation. Please join me welcome Professor Gustav Makula. Thank you.
There's the unmute button. Yeah, thank you so much for that introduction, and it's a pleasure and honor to be here and speak to you, and thanks for allowing me to do so, even though I'm not physically present. So I hope I can still make it engaging and interesting enough for you guys in the room. So yes, I'll be talking on adopting knowledge and models from cognitive neuroscience to enable socially interactive automation. So I will in contrast to Kathy's talk, which was really nice, taking that sort of use driven design perspective, I will instead start from the perspective of we want to put automated vehicles on the road, assuming that that's what we want to do. How do we think about social interaction? And if we think about scenarios like this one, right, a relatively simple one with this lady wanting to cross the road, and there might be one or more automated vehicles out there somewhere. And when they approach the situation, they need to do it in a way that's compatible with these humans, this lady. And there's a number of different approaches to that already being worked on, things like intention recognition algorithms to understand what the intentions of these humans are. Also trying to capture behaviors of humans in virtual agents for simulated testing, and other approaches as well. But the common thing is that basically we need to capture in mathematical models in one way or another, different aspects of human behavior and how humans interact in traffic. And we can do that in different ways. We can approach it as an engineering problem or as a machine learning problem, and all those things are great ways of doing it. But what I want to contribute here is to encourage taking the perspective of psychology and cognitive science and cognitive neuroscience, where a lot of these aspects, a lot of relevant aspects relating to human behavior and interaction have been studied, not necessarily in a traffic context, but I will argue that it's worth looking there for some inspiration. So the main takeaways from my talk, if I'm successful, might be something like this. So I've already sort of said that to make automated vehicles interact well with humans, we need models of human behavior. The thing to think about then, I think, is that human interaction is underpinned by a range of cognitive mechanisms. The brain is behind this stuff, right? For that reason, I think cognitive neuroscience can provide useful knowledge and models about human interaction. I will give sort of 3 examples of important domains of knowledge there that we can sort of tap into. And one recurring theme in those that I think it's worth bearing in mind is that humans tend not to interact with machines the way they interact with other humans. So these will be my main takeaways. But let's dive right in then. The first example, so a relatively basic one, right? If we want to coexist in traffic or in the world in general, we don't want to collide. So we want to be able to perceive risks of collision. So that's something that both humans do, automated vehicles do, but also lots of other animals, right? It's a very basic thing in life. So this has been studied a lot in neuroscience. So, for example, there's some pretty famous old studies with pigeons who saw stimuli like this stimulus coming towards them. So it's looming towards them, visually looming towards them, in the sense that when this object comes closer, the distance decreases, the image of this object will grow on the retina, the angle will increase. And what was found in this research, and which has then been replicated in lots of other animals, is that there are like specific neurons in the brain which are sensitive to this looming. So if a ball approaches in the same way, but just different sizes of ball, this means that the looming will grow faster, the angle will grow faster for the larger ball, and you can find this. This is an example from one given neuron. It responds later for the smaller ball and earlier for the larger ball, in a sense that's consistent with the idea that this neuron is really in charge of detecting a certain level of looming. And if you sample another neuron, it'll have slightly different threshold and so on. So there seems to be quite deep-rooted functionality for this in the brain, basically. And just to sort of insist on that point, you can go all the way back to extremely simple animals, our very early ancestors in the sea, even with just not even an eye yet, just some visual sensors. There's specific neurons in a part of their nervous system called the tectum with this kind of functionality. It's still there if you start having 2 eyes. This is sort of like a hagfish or a lamprey, something like that. If you get to something like a pigeon or an ancestral vertebrate, there's still this tectum in there. If you get to a mammal, there's still a tectum. And if you go to humans, we don't call it tectum any longer. We call it a superior colliculus, and it's in there, hidden deep in all of our brains, these neurons that respond in this exact way. If we put one of you guys into an fMRI scanner and show you looming stimuli, these little guys will light up in your superior colliculus. So that detour via evolution and fMRI scanners brings us back to this road crossing scenario, where in one sense, if I am a pedestrian and I want to cross the road, it's all just about gap acceptance, right? You've probably heard about gap acceptance as a modeling challenge in road traffic. And there's been a lot of research on this, just sort of behaviorally in humans. These are just plots from 2 example studies, one by Lee and one by Lobjoie, different time gaps to an approaching vehicle and probability of gap acceptance by human participants. So as you would expect, the larger the time gap, the higher the probability of accepting the gap. But what is not as obvious is that also humans have this consistent pattern of accepting gaps more readily if the speed of the vehicle is higher, even for a given time gap. You can see here, right? So for 4 seconds time gap, the probability of gap acceptance increases with the vehicle speed. And it's not clear why this happens. I mean, in one sense, you should just look at the time gap, right? If the time gap is large enough for you to cross, you should just cross. If anything, maybe you should be more careful if the vehicle speed is higher, because maybe the collision would be worse, but it's actually the opposite. And the interesting thing here, bringing it back to looming, is that Kai Tian, a PhD student, recently graduated in our group, found that actually you can explain this pattern very nicely by assuming that what people are thresholding isn't really time gap, but actually visual looming. So you can take each of these two data sets with a slightly different parameterization between them, but you can sort of just explain it across these different speed conditions with one single model, just based on looming. So the point, as I see it here, is that this is something that humans do. So when we do automated vehicles that coexist and interact with humans, we should be aware of these kinds of patterns, right? That humans have a greater tendency to engage in risky crossing behavior if the vehicle speed is higher. Kai Tian found that as well. So this should be a part of our models, ideally. And a key point, I think, is that we can't just assume that when we throw our machine learning at our data sets that the models are going to learn these things. We need to go in and check. As a sort of follow-on, I'm not sure if Yu-Yang Wang is in the room. I know he's in Alaska at least. He will be presenting on a sort of follow-on to this on Tuesday in session 05. And there he'll sort of explain that this might make sort of normative sense as well from a perspective of visual perception noise. So tune in for that if you're interested. But okay, moving on. The second example I wanted to give comes into play when you think still about these kinds of interaction situations. It's not only about looking for gaps and so on, as if these other objects are just constant speed obstacles. It's also about what these other guys are up to, right? So theory of mind, this idea of attributing mental states to others. So other road users might have intentions, they might have beliefs about my intentions or what I have seen or whatever. And this is also something that's been studied a lot in psychology and cognitive neuroscience and in animal behavior as well. So you can look at relatively simple animals like this scrub jay, for example. If this guy is hiding this little nut he has found, and he sees that there is another bird watching him at this point, he will later come back and hide the nut somewhere else, because he seems to have some kind of rudimentary theory of mind. He understands that this other, on some level at least, that this other bird has seen him hide the thing and might pinch it from him. But yes, humans do it as well. As we all know, we sort of have thoughts about what others are intending to do. And this has been studied in laboratory paradigms like this one, for example. If you watch a video here and your task is to, as quickly as possible, determine whether this hand is reaching for the small ball or the large ball, you can see over here it's obvious, but somewhere on the way you might be able to start telling. And what's been found then is that there seems to be a quite specific network of brain regions, the sort of mentalizing network that's in charge of this. And you can model the human behavior in these kinds of tasks quite well with Bayesian models, assuming that people are sort of near base optimal in their attribution of beliefs, giving the world states and the actions that they see others taking. So that's a kind of model that we have been adopting in our work a bit. So this is a paper that's soon out. It's available as a preprint already. I'll give you the link later. But where we looked at a bunch of different of these kinds of highly socially interactive scenarios and behaviors that happen in traffic, and we tried to think about what kinds of models do we need in order to explain these various kinds of social phenomena. And we found that we needed a pretty complex model, bringing together quite a bit of different cognitive mechanisms. I don't have time to go through them in detail, of course, but one thing which was in there was this kind of theory of mind about what the other agent is doing and what they might start doing depending on what I do as well. And then we can get simulations like this. These are what you're seeing here is a plot of vehicle position on the x-axis versus pedestrian position. And in this column, it's this kind of scenario with where they're initially on a collision course, but the pedestrian has a priority. And then you can see most of the time the vehicle lets the pedestrian cross first. So the vehicle waits here while the pedestrian is crossing. But interestingly, with these kinds of assumptions in the model, we can start to get these kind of short stopping behaviors, for example, where the vehicle exaggerates its deceleration. It decelerates more than it needs to sort of encourage the pedestrian to start crossing, to be clear about its own intentions. And similarly, we can see behaviors from the pedestrian model that exhibits hesitation while it's trying to figure out what this driver agent is doing. It sort of slows down a little bit, even though there might sort of objectively be safe to cross. It hesitates and then sort of decides to cross when it's understood what's happening. Others have been looking at these kinds of things as well. For example, Olger, who I waved to over the video a bit ago. I know he's talking later in this session. He's been doing some very nice modeling along similar lines as well. But again, the point is that if we are to do socially interactive and successful automated vehicles, we need to consider these kinds of behaviors, both in our human models for virtual agents and intention recognition and so on, but also to some extent in the behavior of the automated vehicles, probably to maybe exhibit some of these kinds of socially helpful behaviors. But I was mentioning at the start that there is also a difference between humans and machines in one way, and one way where that comes into play is in these kinds of theory of mind situation. So for example, I don't know if you know the game Matching Pennies. It's sort of like what do you call it, rock paper scissors, but just with two options instead. So it's basically a game where you need to sort of guess a little bit what the strategy of your opponent is going to be. Here I have an example of a study where human participants played this game, always with against the same kind of opponent in actuality, but the participants thought they were playing against these different kinds of opponents, so a computer or different kinds of robots or a human. And when the participants evaluated these opponents subjectively, they felt that they were sort of different. So they felt that a human is someone who has a mind, but also sort of tries to read my mind. So that human has a theory about me, about my mind. Whereas this one, he looks like he has a mind, but he doesn't look very smart. So he's not really a mind reader in that sense, and sort of opposite for the computer. It might be reading me, but it doesn't really have a mind. But the key point then is that humans were playing the game quite differently, again, against these different opponents. And also the brain lit up in this mentalizing network quite differently, depending on which kind of opponent they were playing. So this suggests that, or it sort of, I guess it suggests quite strongly that this theory of mind behavior that we engage in, our mechanisms for theory of mind get stimulated in different ways depending on whether we believe we're interacting with a human versus a robot. And I think this is something which is relevant in an automated vehicle setting as well. Yes, I wanted to show it in a robot setting also, because there's been these experiments with sort of walking and robots for walking environments, where if you set two human walkers on a collision course, they're really quick at just resolving that collision course. It's very natural. Whereas when we start doing that with a robot, that natural interaction quite easily breaks down. So again, I mean, this can be for various factors, but it seems that one factor might be that it's more difficult to sort of interpret what the robot is up to. And I think this is something that, I mean, people have looked at this to some extent, but I think it needs more research in the automated vehicle context, from sort of how do humans attribute intentions to an automated vehicle versus to other humans. And the third and final example I wanted to go into is prosociality. So again, relating to that example I just showed with interacting with a robot in a walking setting, one aspect might be theory of mind, but another aspect might also be that I feel like actually the other humans have greater rights to my politeness or whatever than a robot. Maybe other humans have a greater right to walking around than a robot. People might feel like that, and if so, that taps into our tendency for prosociality, so our intentions to benefit others. The word altruism was mentioned by Kathy. So this is again something that goes quite deep. These are marmoset monkeys. I just had to check my notes. And this is an example experiment where researchers studied their prosociality. So in this paradigm, only this marmoset over here can reach these trays. There's 2 trays here, and if he pulls the top one, the bottom one goes out of reach. You see he has this handle there, or he can do the other thing, pull the bottom one. And if there is food in one of the plates over on this side, this guy will typically pull the handle that gives himself food. But in this case, there's no food over there. There's just food in one of the plates over here. So all else being equal, this guy will typically tend to pull the handle that gives food to this other guy. He doesn't know him, they're not related or anything, but he prefers pulling the handle that gives food to the other marmoset. So he gets some kind of pleasure or benefit or whatever from this other guy getting food, seemingly. So this has been described and modeled in psychology and in cognitive science, for example, and this kind of model that you might have seen because it's been picked up to some extent in automated vehicle contexts, social value orientation. So whether you care about outcomes or rewards for yourself versus outcomes or reward for the other, basically. And then you can ask people questions about this with questionnaires and such, and you can sort of measure their tendency for prosociality. Are they cooperative, or are they altruistic, or are they competitive over here, and so on. So this is something we've done in our team as well. We looked at it in the context of distributed simulator study, where we connected our University of Leeds driving simulator to our hiker pedestrian cave lab. And you can see that there's a visual representation here of the pedestrian, body tracked pedestrian for the driver, and vice versa. This pedestrian can see the car of this driver participant. So they could interact in this situation. And when they did so, again, we got this sort of situation where if the car is further away when the interaction starts, typically it'll more often play out in the pedestrian's favor. So the probability here is the probability of the pedestrian crossing before the car. But interestingly, then in the situations, you can see these dashed lines here representing the half of the participant pairs where the questionnaires about their social value orientation indicated that the car driver was more pro-social than the pedestrian. The tendency was for the pedestrian to more often go first. So as I mentioned, this is something that has been picked up in some modeling of road user behavior by some teams. And again, I think it's something worth bearing in mind and considering in modeling of human behavior for in contexts related to automated vehicles, for example, to capture individual differences, but also maybe to control the automated vehicle behavior as such. And again, just to make that point, this is something that seems to be sort of quite deep-rooted in the human brain. When people who are pro-social in nature experience sort of an unfair outcome, which is the solid line here, their amygdala that you might be familiar with. Again, so sort of quite not a cortical structure, a much deeper structure in the brain lights up, and again, if people do these kinds of things with machines instead of humans, for example, playing Prisoner's Dilemma, humans will cooperate more with humans than with computer partners. And again, this amygdala lights up in a different way in the two situations. So again, something quite deep-rooted. Yes, and this is just an example then of something along these lines happening when humans interact with a robot. So in this experiment, humans and robots had to sort of work in the same environment where there was this space constriction in a doorway, and the researchers found this thing that I mentioned earlier, that humans tended overall to not want to give way to the robot. Even if the robot was there first, they tended to quite often squeeze past the robot. So they sort of felt that they had greater rights to priority than the robot. And again, I think this is something that isn't fully understood in an automated vehicle context, I believe. So it needs a bit more research. Okay, I think I'm running out of time, but that fits well because I'm at my last slide. To summarize, I've said, and I think probably in this workshop you agree with me, that to make automated vehicles coexist well with humans, we need models of human behavior. And I think it's important to remember that we want to verify that these actually interact like humans. And I've showed you some examples of how human interaction in traffic is underpinned by what seems like a range of quite evolutionarily old, in many cases, cognitive mechanisms. And cognitive neuroscience provides knowledge and models that we can make use of when we're developing automated vehicles, it would seem. And this specific point that humans tend not to interact with machines the way they interact with other humans. And I think this is an area where it would be great to see some more research. So thanks for listening. If you want to read more, here's some links to the key papers I've been mentioning. If you have questions, don't hesitate to reach out to me at any point, or otherwise just raise your hand and ask away now.
Thank you very much for the nice presentation. Yeah, it's time for Q&A. If you have any question, please simply unmute and ask your question.
Hi, Professor Gustav.
Hi there.
Yeah, hi. Very nice talk, and it's very interesting to see the cognitive science and the neuroscience can be used for solving the problems in autonomous driving. So, so it is. I know some. Currently, I'm trying to bring some models in the neuroscience or cognitive science, such like the Bayesian theory of mind or the the free energy principle. So to solve the problems in the autonomous vehicles. So I try, but so I see you have some experimental results and very good conclusions that are aligned with the cognitive science. So could you provide some practical suggestions when applying these models from the neuroscience or cognitive science to autonomous vehicles? I know it is a very big gap between these two communities. I know you are expert in the cognitive science, so could you provide some good suggestions?
I mean, how to actually do it in practice. I mean, yeah, so it is a big challenge, but at the same time, when you start digging into these models of the brain, or these cognitive mechanisms, quite often they are not so far from things that we are familiar with, right? So when you're talking about Bayesian models of human perception, a lot of the researchers in this area have used like Kalman filters for that, and similarly for these theory mind models, they're not exactly Kalman filters, but also this Bayesian perspective, and I mean, a lot of the more sort of reward maximizing models of behavior connect to things like reinforcement learning and so on. So I think even though in one sense the distance looks and feels big, I think it's maybe not as big as one might initially think. So I do think it's a really sort of potentially fruitful way to go, and I can really recommend it. I mean, digging into our papers, I guess, would be one, perhaps especially this one by me and co-authors. It's the one where we've done the most of that sort of pulling in cognitive models and trying to put them together. And yeah, I mean, it's not trivial, and I think there's a lot more to do here. But yeah, I wish you the best in those endeavors, and do feel free to reach out with more specific questions if you want to.
Okay, thank you. Thanks for answers. Yeah.
Any other question? I have a question actually quickly. Yeah, so you mentioned theory of mind, and I was wondering how you look at some of the criticisms that have been cast on the concept of theory of mind. I think there are quite a lot of criticism in literature around theory of mind, in the sense that people say you cannot gain access into someone's mental model, and sometimes there's this idea of cognitive dissonance, where the way people behave is not actually the way they think sometimes. And so it's difficult to model them.
Yeah. So if I understand your question correctly, I mean, you can sort of, so when you model theory of mind, you can take a couple of different approaches. You can sort of ask people what they think about someone else's behavior, right? That would be a sort of direct approach. And I think what you're saying is that you can do that, but maybe that's not actually the same thing as what they're doing when they're then behaving. No, I fully agree with that. I think it's a bit similar to sort of in the gap acceptance literature, where people do experiments on time to arrival judgments, and then assume that the time to arrival judgment is also what then drives gap acceptance, for example. So I think, I think both are probably important. I don't think the way to go is to just ask people how they think about others and then model that and make that your model of theory of mind and assume that that's the truth. I think it's also very important to go all the way to behavior. And what we found in our work was that we needed a sort of theory of mind model to capture the behavior. In this work I mentioned here, we didn't do the kind of thing where we asked people what they actually thought. We're doing some of that research as well, and I think it informs the other modeling, but I do agree that it's also important not to assume that people know how they actually do these things. I agree with that.
Thank you very much.
Yes.
Yeah, in the absence of any other question, we'll move to the next keynote. So
Thank you.
Thanks very much once again for your time and the nice presentation.
Hi, Professor Igor. I have make you the co-host.
Hi
And
guys. Yes, thanks so much.
welcome our next speaker, Professor Igor Gyulchinsky. He's an assistant professor of computer science at the University of Toronto, where he leads the Toronto Intelligent Systems Lab. He is also a part-time research scientist at the Toyota Research Institute. Prior to that, Dr. Gyulchinsky was a research scientist at MIT's Computer Science and Artificial Intelligence Lab and the Distributed Robots Lab, where he was a technical lead of DRL's autonomous driving research team. He joined MIT from the Autonomous System Lab of ETH, where he worked on robotic perception, particularly localization and mapping. Dr. Gyulchinsky obtained his doctorate in computer science from the KIT and a diploma in mathematics from the University of Stuttgart. His research interests involve developing novel robot perceptions and decision-making methods for challenging dynamics environments. He is the recipient of several best paper awards, including at the ACC, the International Conference of Information Fusion, and the Robotic Automation Letters. Now, welcome our next speaker, Professor Igor Gyulchinsky.
Okay, guys, thanks so much. Just checking if you all can see my screen.
Yeah, everything's perfect.
Okay, perfect. Yeah, I'll put also the chat on the side. So if you have questions, I would say just feel free to ask along the way. Yeah, my career with driving is not. It is in some sense not my first career. I ended up with driving. I was not always a driving person. In fact, I wasn't even a roboticist in my PhD. I started doing state estimation, and the first time I encountered robots was at the autonomous systems lab, where we worked on a big variety of robots. This is, for example, a student built drone that was completely built by undergrad students, which was super exciting. Then we worked on autonomous planes. We worked on something that is not a real robot, but that benefits a lot from robotic technology. Back then it was Google's Tango project. And now VR is having some sort of a revival, I feel. And we also worked on later on autonomous driving, but it was only when I came to MIT where I started working full-time in some sense on autonomous driving. And yeah, my standard motivation for autonomous driving is something that at least people my age and older will definitely know, is this is how we imagine autonomous cars, right? We imagine a car that has an even drier humor than its driver, and can do everything you want. And some people say with ChatGPT we're getting there, and I will not talk to this today, but maybe there is some truth to it. But if we look at what the reality looks now, then autonomy now is still somewhere here, that even autonomous parking functions fail, and functions that are named autopilot, when you actually let them run in very dangerous scenarios, their failures might actually be much more dangerous. So autonomy is still relatively far away from where we would want it to be, but we see a lot of progress, right? We have like deployments in big cities, and there you can, in San Francisco, you can use already robot taxis. And a big chunk of this deployment, it is not like this classical AI research where you have one big AI system, but what we have in fact is we have a big, in a modern autonomous vehicle driving stack, with the exception of maybe one or two companies, we have many components that are highly engineered and that have very different design decisions. And today I want to talk about some of these design decisions, particularly in the context of safe interactive autonomy, and in the context of some learning-based pipelines. So what do I mean by this? Autonomy, I think, is clear here. So the difference to classical robotics is that we operate in not perfectly structured environments. Interactive means that it involves multiple agents that are potentially human. So we have to take this into account. Safe, we want to avoid any traffic accidents. And the probably most vague term here is inductive biases. It has many very precise definitions that still leave you wondering what it is. The best definition, I actually like the one from Wikipedia, which is inspired by the original work that introduced inductive biases from Mitchell, which is basically says it's a set of assumptions that a learner uses to predict outputs of given inputs that it has not encountered. And for me, some of my research particularly focused on trajectory prediction, but also later on planning and on inductive biases in this context. And by and large, in trajectory prediction, we have two flavors of inductive biases. We have some more, and I will mention some more, but two are the big ones. One flavor of inductive biases is social context. So how the social context inductive bias is basically, how do we consider the fact that there are other agents around us, and how do we incorporate this fact in our learning pipeline? The way we do this basically has an impact on how our predictors can behave and what solutions, like what predictions they choose out of the many possible predictions. And the other inductive bias that we have that is as relevant is scene context. So scene context is basically the question about how do we incorporate the environment. So how do we tell a prediction system or a planning system that is learning based what our environment looks like, and how do we allow it to learn based on this information. And for all of these works, there are for these two design decisions, in some fact, you could argue that most trajectory prediction papers and some of the planning for autonomous vehicle papers basically focus on these two questions: how to build neural architectures in a way that they incorporate social context in a certain way, and in a way that they incorporate scene context in a certain way. So you will, for example, just to make this point clear, we don't see papers that say by using a very different training set, we achieved better results on the same neural network architectures. And trajectory prediction, most of papers are basically along the lines of by using a different architecture choices, or by reformatting our input, we achieve better results. And they're rarely of the flavor of by using different data, we achieve better results, except that we all know more data is better. But that's it. And as you know, trajectory prediction is actually a very, very hard problem. Particularly, I would argue for driving, it's even harder than for predicting pedestrians, only because in driving, the data sets are even more biased than with pedestrians. I think cars go a much bigger share of their trajectories just straight, whereas pedestrians do, relative to the amount they walk, more changes of directions. At least in driving data sets, I believe this to be true. But they also are biased towards walking straight. So it's very unbiased prediction problem. One of the first ways in deep learning based predictions, we had before other models of how to integrate like social context, was this work which was social LSTM. And the way social LSTM worked was basically having LSTMs for each agent that they predict. Back then, I believe it was only pedestrians, because they used like these very early standard data sets, which were the ETH and UCY data set, which mainly focused on pedestrians. And the way social LSTM worked was by proposing a new pooling mechanism that allowed the LSTM of one pedestrian to look at the inner hidden state of the other LSTMs. So the idea behind this was basically to take into account what other pedestrians do and what other vehicles do. And this paper and one or two more of this flavor sparked off a huge line of research that basically was arguing for a very long period of time, like what is the best way to incorporate social interactions. And I think we are not done here yet. There is still like research ongoing about just discussing what is the best way of incorporating social interactions. And there were different variants to doing this in a lot of different ways. For example, there's this paper, this group, Alahi, had later a paper, Social GAN, and they also used a pooling mechanism. Then there were papers such as Social GAT, where a graph attention network was used to model this. Generally, graph neural networks were very popular and are very popular for modeling social context, because you can basically create some sort of social graph. Even in the social LSTM paper, the visualization already shows that there is actually a graph structure, even though they didn't use some graph networks there. So that's basically the one design question, like social context. The other big design question is scene context. And there, by and large, I would say there are at least 3 different categories of how to incorporate scene context into a trajectory predictor. And I will only name examples. I'm not sure whether these 3 categories are really the first paper to do this. So one example was, for example, the SOPHY predictor. And the way SOPHY integrated the scene was by simply taking a top-down view. This is from the Stanford drone data set, and injecting this top-down view into a CNN processor. And the CNN processor basically then learned some features that were helpful and processed in some attention module and were helpful in predicting trajectories. They still used an LSTM per agent, which you see here, but the general idea for integrating scene context and SOFI was to simply use the top-down view image. Then another idea that was completely different from what people were doing at its time is to say, instead of taking top-down view images, we represent the entire environment, including the agents, as a polyline. And this was the idea of Waymo's VectorNet paper, which is now also 3 years ago. And VectorNet basically literally use polylines to represent agents, which is I think here in green, but they also use polylines to represent lane boundaries or crosswalks. And then they basically modeled it again as some graph, and did also some graph variant of graph neural networks to basically learn predictions on these polylines and to learn how to do it well. They had some cool ideas. For example, whenever these lines were not perfect, one of the tasks that they learned it on was map completion. So this allowed it to better reason also about the trajectory. So there are one of the inductive biases that I will not discuss as much about this in this talk is what are actually good supervisions, auxiliary supervisions to make tasks such as planning and prediction better that have actually nothing to do with planning. And one popular task is some sort of map completion, which Waymo used in their vector network. And finally, another one that goes back to the original idea of top-down view was more along the lines of using, again, a top-down view, but not just a picture, but basically rasterizing the map or rasterizing your sensor data in a top-down way, and then using this as an input to your predictor. So one paper of many papers that are an example for this is the MP3 paper from Raquel's group, which is basically a unified model for doing like multiple tasks. They do perception, prediction, planning, but also mapping and map completion, because one important problem, as you guys know, is like this problem of mapless driving. So how can we drive if our map is not up to date, or if we are in an environment that is not really easily to map? And this was the third like very popular inductive bias for scene representation. But this is not it. So these are like the main design decisions that are usually like in the discussion: how to represent agents, how to represent scene. But there are a bunch of more subtle inductive biases. Starting with the least of this one is probably the integration of dynamics. So Trajectron uses a lot of ideas we already discussed, but one additional thing that they use is that they really incorporate like potential pedestrian or vehicle motion dynamics into their predictor, which is actually only visible here in this integral sign in their overview. So to make it really what they call dynamically feasible, and to enforce dynamic feasibility. And funny enough, like although we are doing like trajectory prediction research now for so long, I feel like we don't still have a good answer to this as well. Like what is the right place to integrate it and how to choose this bias. Another inductive bias is about the algorithmic structure. So one very early trajectory prediction, Desire, had basically the idea of having a so-called ranking and refinement module, which was executed in an iterative way multiple times. And this multiple execution times are basically like a very relevant component there to make their idea work. So they basically have one prediction, it goes through their ranking and refinement module. It's inspired by inverse optimal control, and they basically learn a function that scores the quality of a trajectory, but that also basically provides improved estimate by providing the difference with what comes from the previous iteration step. And this they do multiple times to obtain better predictions. So coming to my personal research, one of the questions that I was curious about is what other inductive biases are missing from this general debate, and how can we integrate existing inductive biases for new or different tasks? And if you look at an intersection like this, like predicting behavior at an intersection like this requires a lot of knowledge. So one thing that these inductive biases that I have shown you so far is missing is it does not know any local norms. So even if an intersection like this looks the same in Washington and in Toronto, or in Washington and New York, what it does not have is, it does not know, any of these previous encodings do not know that people in Toronto and in Washington, or in Boston and San Francisco, behave completely different. San Francisco, Boston, Toronto have a reputation for having terrible drivers, while other cities have a reputation for having great drivers. And this is very hard to encode in an inductive bias. Another thing that so far inductive biases didn't really encode is actually traffic rules. So we had dynamic feasibility, but we did not encode traffic rules. And finally, making some of the inductive biases work that we had in prediction for planning tasks is only more recently gained some momentum. So the first question that I was asking when I started working on trajectory prediction is, how can we learn environmental features in a location-specific context model? And actually, this paper back then, it was my first, I think, one of my first deep learning papers. And I was not that excited about it because I still learned about it. But funny enough, it had one idea that you will recognize if you have followed the NERF literature. We used a coordinate-based network, and or now these days it's called neural field. So the idea that we had is we basically had the idea to learn a location-specific information in a latent map. And we create these maps via a multitask learning approach, where one part of course is supervision, but then we also have auxiliary tasks such as image reconstruction and environment semantics, even though we only had partial semantic labeling available. So the typical way this works is in trajectory prediction, we basically take some trajectory and we inject it directly into the predictor in these coordinate-based predictors. And the thing that we changed, and this change applies to most coordinate-based predictors, is we basically, instead of injecting the trajectory, we also have a so-called context map. And this context map is not a real map. So it's not designed by a human, but this is just a set of location-specific neural network biases. So this context map is literally learned during the training process of the neural network. And learning it during the training process of the neural network means that we now have a trajectory embedding that not just encodes the trajectory, but basically also encodes some sort of location-specific information. And here is the entire overview of our approach. We literally took as our base predictor, we took SGAN, and because back then when I was working on this, it was like the state-of-the-art predictor. And we basically modified SGAN in a way where additionally to injecting trajectory informations, we now would also inject map embeddings, both into the encoder and into the decoder of social GAN. And the cool thing about this is literally, so it works very similar to what some coordinate-based networks do. It literally chooses a path here, but also learns this norm. And the cool thing is it provides really allows for location-specific learning information. And we train this thing, as mentioned earlier, not only on the trajectories. So it's not only the trajectory information gets back propagated, but we also train it to such that it can predict the map image. In our case, it was literally just image explanation. And we also try to use a map encoder to basically be able to decode the image into the context map. the same we do for semantic labeling. So here I think the label was bulkable versus non-bulkable area from a top-down view from the, I think this is the SARA dataset. The UCY dataset from the UCY dataset, the SARA segment. And the interesting, we have some map regularization to ensure that these maps work well, even though this supervision is only sparse. And of course, the numbers back then, it improved upon whatever the baseline was. But the more interesting thing than the numbers is actually the behaviors that it learned. So a regular trajectory predictor that focuses on relative information would not know that here is traditionally a door unless we have a typical annotation for it to be a door. But because we learned in a location specific way, so we literally overfitted to the scene in an idea that is similar to what like in computer vision neural fields are doing. Our predictor was able to learn that it is a typical behavior if someone is going already slightly in this direction, that this person might actually enter the door and go into the store for buying clothes or looking at clothes. And that was basically one way that where we could say, okay, this approach allows us to incorporate some sort of local social norms. And we don't need to encode what the social norms are, but we let the predictor learn the social norms. Okay, the next challenge that we addressed is basically how to integrate traffic rules and behavioral priors into trajectory prediction models. And this is more challenging because traffic rules, there are kind of a lot of them. And even in our work, we just looked at integrating a few of them. And the general underlying technique that we used was signal temporal logic. And basically signal temporal logic, the basic element of it is a predicate, and the predicate is basically an expression that can be evaluated to a true or false statement. And signal temporal logic consists of two main components. One component is basically classical Boolean operators. The other component is temporal operators. And these temporal operators allow us to make statements such as something will be true after a given point or a time step, or something will be true only in one particular time step. And one element of signal temporal logic is a so-called robustness degree, and this or robustness function. And this robustness degree is basically a way of evaluating a given trajectory and a set of signal temporal logic statements and checking whether this trajectory satisfies the statements and to which extent it violates these statements. And here are some examples for how this can look like. So this allows us now to formulate the traffic rules with a function that can even be formulated in a differentiable way. And you guys might see where this is going. So we have here, for example, a stop sign, and we want to be able to express that a vehicle has to stop at this stop sign. And the simple idea, again, is we have some trajectories, we have a base predictor, and we have a robustness layer. So if this base predictor predicts something that is against traffic rules, the robustness layer acts as a correction function and corrects the predictor. Similar to what the dynamics integration or the dynamics awareness did in Trajectron++ for their predictor, our robustness layer basically does for our trajectory predictor. The credit for this goes mainly to Xiao, who was leading this project. He basically looked a lot at like using logic for control, and ended up, as he started working on driving, ended up also integrating it in prediction. And the key idea is that we basically have a differentiable optimizer in our trajectory predictor that tries to optimize this robustness function to reduce traffic violations. And we did some experiments. I'll spare you the details, but the main takeaway point for this for these experiments is literally that it removes outliers from trajectory predictions. So we literally, by integrating this STL layer, we have mostly good predictions, but sometimes if the predictor is off, this type of layer helps with removing very odd predictions and making them much more much more plausible. We also have improved sample efficiency because now we integrate the traffic rules, and the learning burden on the network becomes easier. There is one problem with this approach, though. This approach enforces traffic rules. The reality of traffic rules looks somewhat like this, that a lot of people violate traffic rules. And ideally, we would want our predictor to be aware that not all traffic rules are created equal. And some traffic rules are just violated by people. So the way to implement this in a follow-up work, what Xiao did is we basically just used again for that. So it has a base predictor that takes, I think we use some rasterized representation here, and that has uses color for semantic informations, and also has some rote agents with history there, and some noise because it's again. And what it does is basically it also integrates some kinematics and ends up with predicted trajectories. And then the interesting part happens in the discriminator, which also has an encoder and some map encoding, and then has a feature vector that is used for prediction. And this feature vector is, for discrimination, and this feature vector is augmented with an STL syntax tree features. And these features allow then the discriminator to not only reason about is this trajectory plausible or not, but they help the discriminator by providing information of whether this trajectory violates traffic rules or not. So the discriminator now still has the ability to say, okay, I trust this versus, okay, I don't trust this, but by and large, it is still like a helpful system. And finally, I was very interested in how to integrate this reasoning for decision making in an RL setting. And of course, the coolest thing that you can do interactive decision making is racing. So one approach that we were looking at is how to integrate interactions for racing. And this is like following some of the ideas that we had in prediction, but we took them to the level of model-based reinforcement learning. So in model-based reinforcement learning, we typically have self-play where agents play against themselves directly in the environment. And the idea that we integrated was model-based self-play, which leverages a learned world model to allow agents to compete in imagined games. So basically, each agent now reasons about what the other agent is doing. And in our methods, we basically have high-dimensional pixel input that is encoded into some sort of latent embedding. And this latent embedding is used for learning a policy, one-step rewards, and a value function. And of course, one of the challenges is to model the interactions between agents. In fact, for us, this was the main challenge because our architecture otherwise was based on the Dreamer agent where a lot of the rest is already done for us. And in our agent, the world model is basically learned from rollouts that are stored in a data set of past experiences. So as mentioned, this is similar to Dreamer. And the latent embedding is learned by an agent to reconstruct its own observations and predict its rewards. But additionally to predicting own rewards and own observations, our agent is also trained to predict the opponent's observations from the same latent space. So without having access to the opponent's view. And this allows our agents to learn reasoning about opponent behavior. And ultimately, what we see is that reconstructing their own state is, of course, much easier for an agent, but our agent is also still able to successfully reconstruct the prediction of what the opponent is doing, which you can see here. And as usual in model-based RL, we used in this world model to derive behaviors and learn a value network. Using this two-agent world model allows us for modeling interactions during this entire process, because now the agents always reason about their opponent. And at test time, of course, we do not have access to the opponent's observations. So we can use the opponent's observations for supervision during training, but at test time, we cannot use them. We cannot do any sort of teacher forcing. So the agent's own observations are used to predict the opponent's latent space and subsequently the opponent's actions. And this has super cool results. So of course, it starts with like learning to lane stable driving as so often, but then it learns like aggressive overtaking, learns things such as forcing an opponent off the road, and it even learns to do sometimes pit maneuvers, which is like super cool. We end up with like very, very expressive and vital interactions. Funny background story on this is these last three are learned much later than the first ones. Learning lane stable driving is a much simpler task. So in summary, I would say there are a lot of like very interesting ways and things that we still need to know about the inductive biases that we can use for better prediction and for better planning in autonomous driving. And while the past years focused a lot on like improving a small group of biases, I feel that like the general question, what is the best inductive bias for a certain type of decision-making problem, and what other inductive biases are out there that we still could integrate is not yet answered. And I think we have still like many years of fruitful research ahead of us. And I look forward to your guys' questions.
That's a very good presentation. Thank you so much, Professor Igor Gilichinski. So do we have any questions from the audience or online?
Hi, I do have a question, if I may. So I'm wondering about the discriminator that you mentioned in your setup. What is that? What is the things that you're trying to discriminate against specifically? Because I know, for example, if you talk about discriminator in a particular typical GAN setting to discriminate like realistic or versus non-realistic behavior, it's very likely to overfit. Just due to the fact that there are so many small perks that human cannot notice, but the machine learning algorithm was able to pick out in driving logs. So I just wondering about that discriminator design.
Yeah, no, your question is spot on, and that's actually also a problem that we're facing. So for us, it also tries to discriminate on realistic versus unrealistic. It is super hard to train, and we needed auxiliary losses. What is very interesting about these GAN-based approaches, and I'm not sure whether these days we would have used it, but back then it was a good idea. What is to me interesting about the GAN-based approaches that none of them can make do without an auxiliary loss that is at least like some sort of MSE loss over the true trajectory. And the problem of overfitting in GANs is like in these discriminators is definitely like a very real problem. So the one difference, and it's also a problem for us, the one difference that we do have is basically that we actually help the discriminator by also allowing it to look on traffic rules. So by providing this extra information, we basically say, tell the discriminator, this is an important piece that you might want to look at. And we can ablate that without it, it performs worse, but it doesn't solve some of the general GAN-specific problems.
Okay, thank you. By the way, Igor, great to see you.
Yeah, great seeing you too.
Yeah, hi, Professor Igor, and thanks for your great talk. So I have a question, if I may. So in your prediction paper, so you mentioned like in the prediction task, you need to consider many factors like the interaction and multi-agent reasoning, and maybe the context information, also local scene information. So I'm wondering, like, if it is possible for us to like develop some general method or general model that can capture different factors of all factors of this, and also how can we develop a general model that may not only be used in one specific location or one specific setting, but also generalized to more diverse scenarios or settings. Yeah.
Mm-hmm. So I feel like the way predictors are deployed now, particularly the way AVs are deployed now, they are kind of already very overfit to a specific setting. And the way that I feel you could develop a general model is for areas that you do know and for which you have a lot of data, you can use an approach similar to context map to learn something specific about this area, but at the same time, train your predictor in a way that when a context map is not available, where you can, let's say, integrate some sort of uncertainty, that your predictor does not try to use this type of location information, but just tries to do the best possible job. For example, with some sort of mask and so on. It's a little bit similar to some of the ideas that, funny enough, that we would have seen in conditional nerves, where you don't want to train scene specific, but want to use multiple images as an input for reconstruction. My students started working a lot in this area, and I'm recognizing a lot of similar themes now. So maybe that's why a lot of the examples came from there. But I would argue I would kind of argue that we don't necessarily need a model that is fully general and works everywhere equally well, because even now, like, vehicles are modified to local specific rules. And I don't mean this just at the software level, I mean also at hardware level. So safety rules are different from country to country, which sometimes requires technical modifications to how vehicles are sold. So trying to just have a very general network while we have so much data that is location specific, yeah, I personally wonder whether this is the right goal. It's definitely easier for evaluations, but making use of not making use of location specific information feels almost like a waste, because it basically means we're throwing away the geo information that we have before we start the training. And while this is like desirable, we always want everything to generalize to every area, but I feel like we're losing something if we do this. And that's also not how humans do it. Like humans are also using location specific information. Like when I drive in a new country where I haven't been before, I drive in a different way than driving at home. So yeah, so I guess my advertising is kind of a little bit critical of general models.
Yeah, thanks for the question. Yeah, so the reason why I'm wondering about this question is like nowadays, like the civic models and NLP models, they've been very, very powerful, like the ChatGPT, right? So you can answer different kind of questions, different languages, different settings. Yeah, but it seems like maybe the big data is the cue for everything. So yeah, but for the driving task, it may be more complicated. But yeah, I would agree. Like this, there is always a trade-off between like how much information you use and also overfitting on the setting. So yeah, thanks for the question.
Yeah, I get
Yeah,
your point. Actually, I think we do not disagree. So maybe it is a good idea to train a GPT-like model that is super big, that also involves geographical information. And then as you do execution, you can still say, create this prediction for me using, not knowing that it is that the cars are located in Toronto versus having location-specific predictions. So maybe you can do something like in GPT where you just train a very big one. My main argument is not against this. My main argument is against throwing away geo information.
Okay, yeah, that's true. And maybe we can develop maybe a pretty big prediction model, but with a smart mask strategy, right? So we can mask out what kind of information we get in this specific setting. Yeah, so yeah, we don't know. So maybe when we have more data, we can see if that is possible. Yeah. Yeah, thanks for the answer. It's very inspiring.
That's pretty cool. So let's thank again for Professor Igor Gilishensky for his wonderful talk.
Yeah, thanks so much, everyone, and sorry for going slightly over time.
And now let's welcome our next speaker, Dr. Yin Chang. And Yin Chang is a tech lead manager and a software engineer at Zoox, where she applies planning and machine learning techniques to solve autonomous driving for dense urban environments. She serves as an associate editor of IEEE Transaction of Transportation Electrification. She holds a master's degree and PhD degree in mechanical engineering from the University of Michigan. Now let's welcome her.
Thanks for the introduction. And it's my great pleasure to share some of the work that we did at Zoox here. And so let me share my screen. Okay, so, okay. Thank you everyone for coming to this talk. And so today I will share a system that we built in Zoox for automatic parameter tunings for the autonomous driving system. And so before we dive into those technical details, I also want to give an overview about what we are doing at Zoox. So Zoox have a mission that we are reinventing the personal transportation and through building the personal built vehicles. And we are a part of Amazon. And so like our goal is to build the journeys that can help everyone to enjoy the journeys. And also we build ground up autonomy. And also this shows kind of things we can achieve safer street and fewer cars and less pollutions. And so here, as you can see in this picture, this is our purpose-built vehicle. And it has no steering or pedal, and it's basically fully autonomous kind of design. And you can see that it's quite different from the traditional vehicle. And so it has 4-wheel steering, and also it has a full suite sensors. I will discuss more later. And also it has sliding doors so that it can fit seamlessly into the busy street. And also it has very powerful onboard computer. And also, so another unique feature for it is that it can actually drive bi-directional. That means you can drive front or backward and can switch anytime. So as you can imagine, it will make the parking and also pick up drop off much easier than with current traditional vehicles. And it's much more maneuverable. The turning circle is only 8.4 meters, which is much smaller than other traditional vehicle as well. And also it communicates with sound and light to actually send out interaction information to the other agent on the road. So today is a workshop about interaction. So this is another way that instead of only rely on the algorithm to do the interactions, the car itself can also send out some information to the other agent on the vehicle and on the other, for example, crosswalk, those type of part of the maps to interact together. And also, as you can see, it can also send out the sound signals to identify itself for pickup. So it's also better for the safety. And also the lighting information can also tell the other road users what Zoox will do next. And also it's from the hardware perspective, it has over 100 new designs in terms of hardware. And this is one example. We can see the airbag inside this car is quite different. It's actually symmetrically protect every riders in this vehicle. And it has cushions around the head, the neck, and also the back for the riders. And so our mission is like, it's not just enough to be as safe as normal cars, but we need to be much, much safer. And also from reactive safety to proactive safety. And we call that strategy prevent and protect. And with that said, like recently we deployed this fully autonomous vehicles on road. And this video shows like some of the methods we use to test out these vehicles. You can see like in the windy and in the rainy roads and also in the snowy roads. And also that is mainly on the private track, then like on the public road, doing this kind of testing and also deployment. So currently it has been deployed into California roads. Yeah, so that's kind of an overview about what we do at Zoox. And then I would like to dig into why it really matters to have the automatic parameter tuning system. And so as you guys might already know, it's in the autonomy system, it involves several big pieces. And aside of them, like perception, prediction, planning, and control involves tons of parameters, not only the hyperparameter in the models, but also a lot of like parameters in the rule-based system also involves a lot of parameters. And so our stack has also like have similar kind of architecture in terms of perception, prediction, and planning. And perception have a sensor suite combination of cameras, lidars, radars, and long-lived infrared. And it's capable of detecting, tracking, classifying hundreds of dynamic objects in real time. And also it's having the specific attributes such as gestures, distractions, construction zones, and so on. And then the prediction and planning actually have very close interaction between each other. So as you can imagine, when we actually predict the other agent behavior, it's not only kind of the so-called kind of like passive prediction, but actually we need to do the active prediction. That means the prediction from the other agent need to consider the behavior from the ego vehicles. And so like the prediction stack uses data from perception stack to help infer the behavior of dynamic objects from us, and also simultaneously accounts for multiple versions of future depending on the environment around it. And also that environment also means a part of that environment is created by the ego vehicle, which coming from the planning and control. And also the planning and control need to decide essentially how to execute the mission safely and comfortably, and also responsible for the things like acceleration, braking, and steering. And also it involves low-level controls. And as you can imagine, only this stack, we haven't even talking about mapping, like the other simulation to validate this kind of autonomous. Only these three stacks involve thousands of parameters that we need to tune. And so that brings us to the topic, why we need to have this automatic parameter tuning for the autonomous driving systems. And also I want to share some of the examples to share with you guys how complex the real application look like for deploying this kind of system in the real world. So as you can see in this example, it's in the night, and also it's in, this is a log from the San Francisco busy street driving in the night. And as you can see, we have a lot of cars, and also this is a narrow street, and there's parked cars on both sides of this road. And also you can see a lot of pedestrians on the different parts of this crosswalks. And also when the ego vehicle turning left, it also involves interaction. There's another vehicle is going straight, and also a lot of cars is basically parked tightly. So there is only a narrow gap to proceed here. And as you can see, like actually the margin is quite small to fit into this kind of street. So to handle this kind of examples, and this is just like one of millions of this kind of scenarios on the real world, and there involve thousands of parameters need to be tuned so that all the different kind of stack in the autonomy can interact with various different type of agents in the real world. And it's very challenging, actually. If we take a look at this example again, we need to firstly ensure safety, but we also don't want to get stuck into this narrow street. So it needs to involve like balance between safety, progress, and also comfort, because we have really like human riders on the vehicles. And so what we are building here is automatic parameter tuning system that can be used, a generic one that can be used across different tasks for the autonomy system. And also not only the online autonomy system, but also the simulation parameters that we use to test out the whole stack. And so how does that look like in the top kind of the high level view? So it's to find a set of optimal parameters automatically to improve the engineering efficiency and more importantly, improve the driving behaviors of our autonomy deployed vehicles. And so it starts with the parameters that we select to tune. And then it goes through the distributed simulation system. It's a large scale distributed simulation system. And then it extracts the metrics from those simulation. And here, when we talk about the simulation, it can involve different type of simulation. It can be the offline simulation, the so-called traditional simulation. It can also involve the virtual reality simulation, where you put that car on the private track, and then you inject some virtual agent to simulate the kind of adversarial behavior from other agent to see how the ego vehicle react to those kind of interaction scenarios. And then from those metrics extracted from those simulation, then it goes through the optimization, and the optimization proposes another set of parameters to try. And then this kind of loop goes on until it satisfied the tuned parameter satisfied certain criteria. And so how the framework look like? So it mainly involves 4 components. We call that trainer, which is mainly essentially the parts that help us to propose new parameters and doing the large scale kind of the evaluation. That is, we are leveraging the retune framework. And then it goes through the evaluator, where it's essentially doing kind of the evaluation on the metric side and extracting all the metrics that we needed to extract the final score. And then the data server essentially saves all the scenarios. Then we need to do this kind of test. And the logger essentially log all the information during this kind of tuning process so that we can have a easier introspection of the results and also debugging process. And so as I just mentioned, this is a very generic auto-tuning framework. So that means we need to build this kind of framework that is generic enough and easy to fit into different use cases. And when we look at this evaluation part, we take one simple example just to evaluate one single scenarios. And the blue box are the portion that essentially fit into different use cases. All the other green part is generic. And so for one piece of evaluation, you have parameters where are the parameters that selected from the autonomy stack that need to be tuned. And then have one piece of data. That data means either a log or either a test on the private track. So any kind of like data from that. And also it can come in from the synthetics data as well. And then it uses those information to go through the simulation stage. And the simulation, after simulation stage, we can extract remote metrics from that. And then we can actually using those metrics to calculate some objectives that we want to optimize for, and then get a score from it. And so when we use like, for example, different type of applications, then some changes along those box, the blue box, can be used to change so that it can fit into different use cases. For example, maybe the perception want to improve recall rate, while the planning maybe want to, let's say, improve some comfort score, so they can do some customize there. And so regarding the optimization stage, that is core for this auto-tuning framework to work. Actually, it's quite flexible. it's more like a plugin kind of module that you can use different type of optimization algorithm. For example, the Bayesian optimization like AX, Dragonfly, Sky optimization, or evolution strategize. And also, it also supports the different constraints on the parameter and metrics. For example, when we tune, let's say, tune some parameters, we don't want to have any essentially collision among all the simulation. Then we can put the constraint as kind of like collision score equals to 0 as constraint there. And also, for example, we also want to maybe set constraint on some parameter, essentially the range where we want to tune, right? For example, for some parameter, we kind of know the rough range for it, so we can directly put this constraint there during this optimization process, and it can support the multiple objective optimization together. As I mentioned, for example, sometimes we want to do the optimization among safety, progress, and comfort, so we can combine them together as a total score. Then it involves a trade-off between how you give the weight among those three objectives. But you can also turn it into a multiple objective optimization problem. So among that kind of optimization framework, here it's essentially having this diagram shows kind of the process around that. So the search algorithm can propose the different set of parameters, and so like and then those different set of parameters, as we mentioned, go through the evaluation stage. And in each set, like we use millions of scenarios to test it. And also, for example, here it's the data server can fit into the fixed set of scenarios, or it can dynamically identify some adversarial scenario to test on against. So it's also flexible. And then it goes through the evaluator and score, and then score feedback to the search algorithm so that it can use that score to determine what should be proposed in the next iteration of the auto tuning. And then we have some termination stage to terminate the optimization process, so it output best config the parameter settings. And so also, like among those things that we need to introspect the results, it need to be have a user-friendly interface for the users to identify, okay, where is actually the range of the parameter that we should choose. And so this is a visualization of one of the plots that we use quite frequently, the parallel coordinates plots for our trials. And each of the y-axis represents one parameter that we want to tune, and then the range. As you can see, the range of each y-axis is different. That corresponds to, for each parameter, we give a setting of the range that we want to tune. And as you can see, the objective here, the smaller objective means better. So as you can see, there's purple area among all the different scenario, like the parameters, and we can see that actually there is a region where it leads to a best combined performance. And also some other visualization, for example, we can also see how the objective values involves with the trial number changes. So for example, like we can see that the objective decreases significantly when it goes through just 100 iterations there. And then here also, like there's other visualization where you can use, for example, understand the importance and correlation between different parameters. And also here, like there's also kind of, you can see, okay, from which trial, which is give us best solution, and how does that different in terms of different metrics, internal metrics that we got, so that we can have better understanding to some like the trade-offs and some like introduction of the results. And so with that said, I want to go through one use examples, which might be a very familiar examples to planning folks. So that is cost waste for essentially the cost function tuning for a planner. So essentially, you know, like in the planning stack, either it's sampling-based planner or tree search-based planner or other optimization-based planner, people normally have cost function there. And there, like essentially among the cost function, there are different terms inside for each terms in front of it. Normally it has a weight, but how do you choose those weight? It's very, actually, it's very important for the weight to actually to determine the overall driving behavioral quality. And so here in this example, we want to have a tuning objective, essentially give us best safety, progress, and comfort metrics aggregation overall score. And the training data set we use is large-scale driving logs. The driving log here means that we collected essentially those videos that we collected from the testing of autonomous driving vehicles. And also there are synthetic scenarios. As you can imagine, some of the very dangerous situations that we normally don't encounter during the real world driving. So we generate synthetic scenarios based, and so that's from this training data set, it can have enough diversity, but also enough adversarial scenario to make sure that when we like tune in those parameters, we don't have any regression on the super critical scenarios that like maybe, like so once after 1 million miles, that type of dangerous scenarios. And then, as I mentioned, the tuning parameter for this example is weights for each terms inside the cost function. And we also use two type of algorithm. One is Bayesian optimization, another one is evolution strategies. And so here I want to go through some of the examples before the auto tuning and after the auto tuning. So here is scenario where the Eagle vehicle need to handle the narrow corridor where the Eagle is turning right on the constrained corridor with a parked vehicle and a stationary vehicles. And you can see before the tuning, it basically getting stuck. It's just like so hard to get fit into this narrow gap, because as you can imagine, like we normally have some safety margin to different type of vehicles. When your safety margin is set too conservative, then it gets stuck. If it's too aggressive, then it's getting too close, make that comfort is not good. And so here you can see, like after the tuning, it fit well into this kind of scenarios. And this is, again, this is just like one of the tons of scenario that we use to tune these parameters. So that means when we tune this parameter, it can do better in this kind of scenario, but it didn't really have the big regression or have regression among all the other millions of scenarios. And this is another, let's take a look at another example. So here is vehicle that need to essentially handling a vehicle that which is does a 3-point turn ahead of Eagle vehicle. So what does 3-point turn mean? Like we can take another look here. So essentially the other vehicle is doing this kind of 3-point maneuver that to try to essentially go into the different direction basically. And as you can imagine, in this kind of scenarios, the prediction could be really challenging to predict the behavior for this 3-point turning vehicles. And also for Eagle vehicle, we need to keep kind of a safe distance from it and also not getting stuck. So as you can see, before this auto tuning, it's basically getting very close for that other vehicle. So this kind of interaction happen quite often in San Francisco, but getting those kind of the prediction and handling between this kind of interaction to work well is quite challenging. And here you can see like the vehicle getting too close to this vehicle, and which makes the riders on our Eagle vehicle not feel comfortable, but also the other vehicle might also feel very strange when getting so close, and it don't have the buffer for it to do the kind of like the complex maneuver. And but after we tune it, we can see that it kind of giving a reasonable distance, and also it didn't even need to it didn't even need to get into stop. As you can see, like it's actually just yield and then proceed. And another example. So here it's handling of the left turn. And as we can see, here is where Eagle need to doing Eagle car is this car, and it need to interact with this orange car and through unprotected turn. And this one is where we totally didn't tune this parameter related to the unprotected turn behavior. And you can see the Eagle vehicle just getting too close to the lane boundary, and it's basically in running to collision with the other vehicle in simulation. And when we actually, after tune it, you can see it actually yield and proceed nicely and smoothly. And so those three examples are actually coming from the same auto tuning, like kind of the same auto tuning task, where we just tune those parameters together, and you can see it handle those kind of corner cases scenarios quite well altogether. And so let me give a kind of a brief summary about this system. So it's a generic framework and platform for the parameter tuning for different use cases. And also it's a scalable framework so that it can use large amount of scenarios to do the auto tuning and validation. And as you can imagine, this is a quite parallelized system. So when you scale up the computational resource in the offline setting, and then it can scale up the amount of scenario you can use for testing and tuning those parameters. And it's modularized architecture, for example, that optimization module, we can actually leverage any state-of-art optimization algorithm to plug into that module for better optimization or better process of proposing those new parameters. And also this is a configurable objective matrix that can be used for a wide range of use cases. For example, the one that we just mentioned, like the comfort, object, progress, and safety aggregated objective can also use for a wide range of use cases. And then for some special use case, people can also customize that kind of the tuning objective. And it's also, as we can see, it's also have a user-friendly end-to-end interface for experiments, visualization, and analysis. And another thing I want to highlight here is that, as you can imagine, when it's having just one iteration of the L2 tuning, it's very similar to the large-scale simulation. So this can also kind of leverage any large-scale simulation platform that we can use either internal or externally. Yeah, so that's my kind of like the talk for the auto tuning system. Welcome to any questions. Thank you.
Well, this is a wonderful presentation, and any questions from the audience?
Hi, Dr. Yin Chang.
Hello.
It's very
nice
interesting to hear some talks from the industry level. And actually, I've heard about Zoox several years ago when you just finished the first field test in California. So I'm wondering that the algorithm that you said about tuning, is it used in the real road applications of your Zoox vehicles, or is it just in the validation level?
It's actually used for the vehicle thing. So essentially the parameter that we tuned from this system is deployed to the on-road kind of like the application directly.
Oh, yeah.
And actually
okay,
we need to do that. Otherwise it's just too much work to tune. Yeah.
Yeah, that's very interesting. But you said that that tuning can be used for different cases and scenarios, but in the real environment, there are a lot of scenarios or the cases for the vehicles. So in this case, when do you think it's a good time to do the auto tuning part in the real applications of the vehicles?
Oh, I see. So just let me rephrase. Are you asking like when do we essentially trigger the auto tuning, right? Because every day you encounter so many. That's a good question. So we have two type of trigger for the auto tuning process. One trigger, as you can imagine, is kind of every release. For example, either weekly or like twice a week, where we combine all the different pieces of like changes, right, from different engineers. Then we combine them together to do another set of tuning so that the new like the new changes fit well together and also fit well into the existing autonomy algorithm, right? That is one type of trigger. Another type of trigger is, let's think that when we, let's see, use that example that I just shared, we have the cost function, right? Let's see when we want to introduce a very significant cost terms. Let's see, for example, let me just, I couldn't share too much detail about the internal implementation. So I will use a very simple example. One example is, let's see, we want to introduce one significant cost terms that correspond to interacting this vehicle. And we know that it will affect the overall cost function significantly. In this case, essentially we need to work together with the engineer who implement that cost terms. So when that cost term is added, we also doing this auto tuning all together. The engineer implementing that specific cost term. So when we deploy, we basically deploy that additional cost term and all together with all the newly tuned cost weights to combine them together and then release that together. Yeah, so mainly two type of trigger to trigger this auto tuning. Of course, we couldn't afford like doing this auto tuning for every small pieces of change into the autonomy system. Yeah.
Yes, very clear explanation. And I also have another question about it. It's more general. So basically, as you said, there is one picture in your slides which shows the normal direction of the autonomous vehicles, which is from the perception, the prediction, then the control level, right?
Yeah.
But recently, there are some like autonomous vehicles companies like Tesla, FSD, they're trying to develop a totally end-to-end system, which almost skips the motion planning level. Like if you keep a close look at the recent update on the FSD, they said that they are going to use a totally end-to-end model later this year, which is from perception directly to the control level. That means that the algorithm of FSD receives the perception from the sensors and then directly gives the output control actions for the vehicles. They skip some like motion planning and the prediction stage in their algorithm. So what do you think of this kind of totally end-to-end model for the autonomous vehicles? Are they too aggressive, or like they are, you think, a necessary step to the next level of autonomous driving?
Oh, that's a good question. So I couldn't speak in the kind of like, the broad level. I can only share my personal like view. And again, this doesn't represent Zoox or any company. It's just my personal view. I feel like that direction might be some direction that's will be kind of possible in the long run, probably. But as far as I know at this stage, to have kind of clear output, at least be able to introspect the output from each stage is very important to guarantee the safety. So possibly, like the end-to-end learning can actually give the cars reasonable driving behavior in most scenarios. But in some scenarios, let's see the prediction, kind of like the latent space prediction. The implicit place prediction didn't do reasonable well. Then how to introspect that kind of things and how to improve from that. Because when we're talking about learning system, we need to understand where the learning stack didn't work well, and then to identify, for example, either some data missing, adding additional data, or improving the architecture to improve that. So from that perspective, I feel like the end-to-end learning could be very challenging for the real application. But that's, again, my personal view. Probably in the next few years, when we have big breakthrough in the learning, general, the community, maybe it will become more realistic to achieve that. But yeah, that's kind of my personal view on that.
Yeah, I totally agree with you. I think this kind of end-to-end model is a little aggressive to the autonomous vehicle. That's why Tesla FSD got banned for the American DMV for some time this year. But I think one advantage of their doing this is that they have the largest data, which is much larger than all other companies like driving data. So they can use it to train like something like the large language model, a very large model and we all see like with so many like billions of the parameters, the model may show some kind of the intelligence, like just like the GPT-like model we see this year for the large language model. So they kind of want to transfer this kind of like intelligence to like autonomous driving models, use those like very large data. So that may be possible, but I also think incorrectly it is kind of unsafe and in some way. So very thanks for your presentation and your answers to your questions. Thank you so much.
Thank you so much. Thank you so much for the great
Let's,
questions and
thank
discussion.
Dr. Yin Chang again for her wonderful presentation.
Thank you. And nice to see you, everyone.
Let's welcome our next speaker, Dr. Yuxiao Chen. And yeah, you got the co-host. That's great. Dr. Yuxiao Chen is a senior research scientist in the Autonomous Vehicle Research Group at NVIDIA. His research interests include safety, autonomy, motion planning for autonomous vehicles, especially policy planning and generative AI for closed-loop simulation and scene generation of autonomous vehicle. He did his undergraduate in Tsinghua University, obtained his PhD from the University of Michigan in 2018, and was a postdoc at Caltech from 2018 to 2021. He joined NVIDIA Research in 2021, and let's welcome him, his presentation.
Thank you for the introduction. Just to be clear, can you guys see my slides and hear me? Is there anything wrong with the presentation?
Yeah, everything's perfect.
Okay, cool. Okay, thank you everyone for joining my talk. So today I'll actually talk about the more practical side of the autonomous driving, which is how do we handle prediction and planning. I think Igor has already given a very good talk about this topic, and then particularly he was focusing more on the prediction side. So my talk will switch to the planning side and see how can we sort of conclude and what can we learn from the current approach about prediction and planning. So yeah, I think it's nice to follow from the previous discussion, which is about whether end-to-end is the new norm. What do we think about it? But then I think the traditional way of doing autonomous driving is still via this sort of three-step process where we do perception and then prediction and then finally planning. So when we look at prediction planning, obviously everybody noticed that for the past, I say, 4 to 5 years since, for example, papers like social LSTM, we have seen a lot of deep learned prediction models sort of storming, taking over the field and then pushing the state of the art of the prediction precision. So I'm sure a lot of you have seen this kind of tables and in a lot of places where people are comparing the two key metrics called AD and FD, basically measuring how accurate the prediction model is. But then the ultimate question we actually need to be asked is does this ultimately lead to a better motion plan for the autonomous vehicle? Because as far as I'm aware, probably the sole purpose of prediction in at least AV, right? I'm not saying about other applications, but in AV, the sole purpose of prediction is to serve planning. So really can we lead to good coastal performance is the ultimate question to be asked. Now, this talk would actually focus on one specific concept that we have been pushing, which is policy planning. So let me start with a motivating example. There's no restriction of how prediction should be consumed and what kind of modality it comes out of. But typically, right, other than very few cases where they're using directly a cost map generated by the prediction model and then directly use that cost map for prediction. Sorry, for planning. Typically, what we're talking about is multimodal trajectory predictions, and that's sort of the norm of the current prediction. So if we look at this simple example where we have a red human driving vehicle on the second lane, and then there's a blue autonomous vehicle trying to pass by, which should be a very easy task, but a typical multimodal prediction model will probably give you something like this, where excuse me, there's a major mode of maintaining the current lane, but then there's also a possibility of lane change to the left and to the right. So of course, then the question we should be asking is how do we consume these multimodal prediction? Well, we can consider only the most likely mode, in which case is the maintaining lane mode. Then we might be naive and then sometimes get caught off guard because if the red vehicle indeed tries to do a lane change, then that may actually cause danger. Right? Or we can consider all modes, in which case, obviously, the plan will be very conservative, and then the autonomous vehicle might not be able to pass by the red vehicle, which shouldn't really be acceptable for commercial AI, for commercial AV. So, and then of course there's the middle ground, which is using some probability threshold to kind of filter out unlikely modes, and that is prone to a lot of tuning. So maybe what Dr. Chang Yan just presented might be useful to tune those parameters. But then you have to consider like all scenarios and all cities, and people have different preference. So in general, this is a very tedious engineering process. So the ultimate kind of problem here is that when prediction horizon gets long, right, uncertainty and multimodality will grow out of control, and that makes planning difficult. So our intuition is that actually from how human driving works. So usually human decision making is the sequential process. We don't directly just output multimodal predictions for the other agents, right? So if you look at this typical multimodal prediction, really what's the thought process, it should be something like this, where it's like, okay, the red vehicle may have two choices if in case he wants to either maintain lane or change lane to the right. Or we don't consider changing to the left just for simplicity because it doesn't concern the autonomous vehicle. So we don't really think that a human vehicle would just roll a dice and then decide, okay, 80% I'm gonna stay here, 10% I'm gonna change lane. But instead, it's really a decision-making process that happens sequentially, where in case he wants to change lane, he or she may first nudge right a little bit and see the behavior of the blue vehicle. In case the blue vehicle yield, then it will proceed with the lane change. Otherwise, he might just abort and then avoid collision, right? So this is a typical kind of human decision-making process. So the real problem with the current path planning or motion planning is that if we only search for a single optimal trajectory, we're ignoring all the future observations. In other words, it's almost like we made our mind and then we drive blindfolded for 3 seconds, for example, if this is a planning horizon. Of course, people would say, well, we're doing replanning all the time, but really replanning is not really the solution, because every time you replan, you're still doing the same thing. You're assuming that we will commit to the 3-second trajectory that we're planning for the next 3 seconds until the next time we replan. So we're still not fully utilizing all the future observations that we don't have yet, but then in fact we can enumerate. So this is the really counterintuitive part, is that we can plan a tree structure motion policy by by enumerating possible future observations, although we don't know them yet. So then I'll talk about some examples of the policy planners that we have been developing. But before I talk about it, I first want to sort of talk about briefly talk about the upstream, which is prediction. So some of what are the properties or features needed for policy planning from the prediction side. So the first property that we care about is thing-centric. Now, obviously, if you look at the early literature of prediction, like social, a lot of them are actually node-centric in the sense that they're predicting trajectories of individual agents one by one, and there's no characterization of their joint trajectory prediction, which is obviously not a good thing for planning, because in planning, when we reason about how the autonomous vehicle navigate through a crowd of vehicles, we're always talking about the whole thing together, like and especially when we talk about multimodal prediction, all these modes should be on the joint trajectory of the whole thing. So that's what we call thing-centric. A second thing is multi-stage. In other words, we're predicting during our prediction horizon, we can separate them into several stages and then reason about different behaviors, different multimodality in different stages. The third one is called ego conditioning, which means we can condition the future prediction of other agents around the ego based on the ego future plan. So we don't have a fixed future plan, but let's say we can hypothesize, okay, so what if the autonomous vehicle take this action in the future, then what would the environment react to that? So I think this has been mentioned previously in previous talks of this workshop as active planning, active prediction, if I'm not mistaken. And the last one is differentiable. So can we have access to cheap gradient evaluation of the prediction module? So obviously these four doesn't have the same weight, right? I would say thing-centric is probably needed for most planners if you want to do proper planning. Multi-stage is actually, I'll later show that this is needed for policy planning because really the core of policy planning is to utilize future information that we don't have now, but we can enumerate. So if you don't have multiple stages, then there's no way to do that. Ego conditioning has been shown to improve prediction precision, but we will also show later that this is also very helpful for the closed loop performance. So it's a very desirable feature. And finally, differentiability is really needed for gradient-based planners only. Okay, so the first policy planner example I'll show is called branch MPC. Excuse me. So in this case, we start with a prediction model that is analytical. So it's a lane-based prediction model, and it actually satisfies all four of these. It's thing-centric, and because we're using, and also since we're using handcrafted modes such as braking, maintaining speed, so it's also differentiable. And then all these modes would, so it's also multi-stage, which is easy to do when you have an analytical lane-based prediction model. Now, ego conditioning happens because we actually calculate the probability of the mode based on the risk of collision. So that risk of collision also concerns the ego vehicle, and that's why the probability will change with the ego behavior. So that's how we kind of add ego conditioning to it and differentiable. So now we have a multi-stage prediction model. Then the output it generates is actually a scenario tree instead of several multimodal trajectories. And what we call this a scenario tree because it's really a tree structure describing how the scene evolves over time. And several things should be noticed here is that, first of all, each node here concerns a joint trajectory prediction of the whole thing. It's not really the trajectory of a single agent. The second thing is that we have branching node and non-branching node, and every time we have a branching node, we branch, so that kind of marks our stages. And the reason to have non-branching node is just to balance the complexity and expressibility. If we have every node to be branching, then the tree will quickly grow out of control, and then computation-wise, it's not scalable. So So then we draw inspiration from this min-max branch MPC, which was a quite old paper, where instead of optimizing over the worst case behavior, we're actually minimizing the expected cost over branches. So obviously this is a non-linear, non-convex MPC, so we have to linearize everything. For example, dynamics constraints, linear constraints for the vehicle dynamics, and also non-linear constraints such as the collision constraint and lane boundary constraint. And also we're linearizing the cost. So here I want to especially emphasize that since we're minimizing over the expected cost over branches, so basically it's an inner product between the so basically for every branch we're multiplying the cost for that particular branch with the probability of that branch. And when we linearize that cost, it gives us two terms. The first term is saying, okay, so given the current cost of the branch, how can we change the probability of this branch or I should say change the probability distribution over multiple branches so that we can get a better cost. For example, we can use the ego behavior to make to give more probability to the branches with lower cost so that our overall cost is minimized. And the second term is really just given the current probability distribution, how can we actually minimize the cost of each branches? So this actually gives us the nudging behavior that we'll see before that we'll see later in the simulation. And then actually, if you look at the min-max branch MPC, that was our inspiration, and our what we call it contingency branch MPC. You can see that the only difference is that what they're minimizing the worst case, we're minimizing the expectation, and we both use branching. But then if you even go further, without branching, really what you have is just stochastic control and robust control, right? So yeah, what they're doing is, let's say this particular branch is the worst case, and they only care about this, but pays no attention to others. And what we're doing is we have weights, because we have a probability characterization over the scenario tree, so we have weights over each branch, and then we are doing the expectation. But then if you think even further, really the worst case and expectation, they're really both special cases of a risk measure. So for example, if we take this conditional value at risk as an example, this is defined as the mean value of the alpha worst case outcome of a stochastic process. So if you take this alpha close to 0, right, by pushing this line close to the tail end, then what you really get is just the worst case. Whereas if you take this alpha to 1, then you contain the whole distribution, then what you get out of it is just expectation. So really what we're doing is not that different from the min-max branch MPC in the sense that we're both optimizing over a special case of the risk measure. So the natural thing we do is that now we can use this alpha as a tuning knob, and we can change our focus more on the kind of expected cost, or we want to be more risk averse. And we can show that this kind of branch MPC with this nested risk measure can be formulated as a second order programming by utilizing the dual formulation. I'm not going to talk about detail here, but and the solve time for this comparing to the original QP SQP formulation is very similar. I think this is only like 10% more computation time comparing to the SQP. So let's look at some examples. This is a motivated example where there's a car trying to pass by a car on the adjacent lane, and this is the solution of a single sort of the traditional path planning, where we were planning a single trajectory and we're avoiding all modes. Obviously, you see that it cannot pass by the vehicle. And this is our branch MPC where it's planning a tree and then eventually it's able to finish the lane change. And you can see this is showing the probability of the first stage. Remember, we have more than 2 stages, but in the first stage we have 3 possible modes. I think these 2 are maintaining speed and braking, and this one is lane change. So you can see through the nudging, right, the ego vehicle forces the probability of the lane change to be very low, and eventually is able to pass. So another example, merging, where it's interesting to show that here we have two modes. One thing is the blue vehicle would maintain speed. Otherwise, the other mode is that it will break. And you can see this is a snapshot of the prediction the solution of the branch MPC, and these arrows are plotting the acceleration. So really at this moment, basically it's saying if the blue vehicle would maintain speed, then it will decelerate, it will brake, and then let the blue vehicle go first. So that's yielding. Otherwise, if it's if the blue vehicle is slowing down, then it will accelerate and then actually cutting in front. And this is also showing similar, pretty much the same algorithm applied to robots. Of course, this is less relevant, but then it's showing it has a wide range of applications. Okay, so I just talked about branch MPC. It's great, it works well, but then it also has the requirement of being differentiable, which is usually difficult to achieve when you're talking about deep learned prediction model. So our subsequent work is really trying to tackle that. We want a prediction. We want a policy planner that is compatible with prediction that are deep learning based. So this is called TPP, tree structure policy planning. Yeah, like I mentioned, we want to be compatible with deep learning prediction model. And the key idea is to reduce the continuous problem to a tractable discrete MDP via construction of two trees. So we have an ego trajectory tree, which is pretty much the same, except now we're using deep learned models. And then we have an ego trajectory tree for ego trajectory options. So instead of doing MPC, now we're doing sampling-based planning. So here's the overview of the algorithm. We start with the typical kind of input of the prediction model. We have row geometry, agent history, etc. And then we pass that through a prediction model to give us a scenario tree, very much the same process. And then we also have an ego motion sampler that's taking some of the lane information to generate a trajectory tree that represents the possible trajectories that the ego can take. Now it's important to show this arrow where we're using ego conditioning. So these scenario trees are actually ego conditioned scenario trees, and I'll explain later what that actually means. So once you have these two trees, we formulate a discrete MDP, Markov decision process, and then solve it with dynamic programming to get the ego motion policy. So yeah, really, I think a lot of the methods are pretty straightforward. So I'll skip some of the details. For the ego motion plan sampler, we use spline sampling to generate the ego trajectory tree. And then we are able to modify a lot of the popular sort of prediction models, multimodal prediction models into multi-stage ego condition sync-centric models that generate scenario trees, because these are really the key features that I mentioned before. And I'll specifically talk about what ego conditioning means. So for example, if we have a ego trajectory tree that looks like this, right? Then what ego conditioning means is that first we take this branch, right? And then we generate a scenario tree. And then we take the second branch and generate another scenario tree. So each of the distinct branch for the ego from the root to the leaf is considered a different ego trajectory. And then we do this one for the third one, so that we have an ensemble of scenario trees conditioned on different ego trajectory candidates. And the number, if you don't do any pruning, basically the number of scenario trees is equal to the number of leaves in the ego trajectory tree. And then we can combine these two trees to formulate a finite horizon MDP. So here the state is the joint or the product of the trajectory node and the scenario tree node. So in other words, what trajectory you are currently executing and what's the environment look like in the scenario tree. The action is the next trajectory tree node because that's what we can decide. We can let the eagle execute one of its children next branch, and the transition is stochastic in the sense that while it's deterministic for the trajectory tree, it's actually stochastic for the scenario tree because the environment can follow different outcomes, and then it's actually given, the probability is actually given by the prediction model. So then we can do Bellman equation, typical optimal control stuff, and get the policy, get a policy in terms of a tree out. And critically here, we're showing the Bellman equation without eagle conditioning. But what we're able to show is that when you have eagle conditioning, you have an ensemble of scenario tree rather than just a single scenario tree. And as long as these scenario trees satisfy a condition called causally consistent, in the sense that, let's say you have multiple stages and you can condition the generation of these trees based on different eagle trajectories. If you condition it on 2 eagle trajectories and they agree up to, for example, the first stage, then your prediction, your eagle condition prediction should be exactly the same up to that stage, which is really just causality, right? If you don't condition on different eagle trajectories, then your eagle condition prediction should be the same. And we were able to show that if this ensemble of easy scenario trees, if they are causally consistent, then you only need very minor change to the Bellman equation. You only need to solve the Bellman equation once, and what you get is actually optimal. And basically you can get the optimal policy the same way as you do without eagle conditioning. So we did experiment and evaluation, and in order to show kind of the applicability of our approach, we use 3 very different prediction models. We have a rasterized CNN-based model. We have a UNet-based prediction net, which is going from image to image, and we have a vectorized agent-former, which is a transformer-based model. So we modify these 3 models to make them multi-stage, and apply TPP on all of them. So we do closed-loop simulation, where the eagle vehicle follows the TPP or some baselines, and everybody else follows bits, which is our own deep learned model for traffic simulation, specifically learned for specifically trained for the purpose of closed-loop simulation. The baselines are robust TPP, meaning so everything else stays the same. For example, the eagle trajectory tree stays the same. The scenario tree stays the same, except for the last bit, which is how we do planning. So for TPP, we use this dynamic programming to get a tree policy. For robust TPP, we basically say, okay, we don't do dynamic programming, and then instead we're looking for a single trajectory in the trajectory. We're looking for a single trajectory for the eagle vehicle from this trajectory tree, so that it considers collision over all the possible modes of the environment. And greedy TPP simply means you only consider the most likely modes. And non-EC TPP means we still do this tree planning, but then we don't do a yield condition generation of the scenario tree. So here are some simulation in bits. This is using new things data set, but we only initialize the thing with the new things and using their maps, but the rest is actually just rollout of bits. And you can see some pretty interesting behavior of the eagle vehicle. So you can see that this vehicle with a lot of the tree structure is the eagle vehicle, and then the tree is actually the eagle trajectory tree. You can actually find more simulation results in our website. And what's more interesting is the quantitative result. So we use 3 metrics to measure how good the planning is performing: crash rate, obviously, off-road rate, and also coverage, where coverage simply means how much area you're covering through the simulation, so that it's a measure of liveness, right? If you stay there, if you stay at a position forever, then you don't get a lot of coverage. So the first finding is TPP significantly outperforms non-policy baselines. So comparing to the robust or greedy variant, right? TPP significantly outperforms them in all three metrics. And second thing is TPP with deep learned prediction model outperforms analytical baselines. So if you don't use deep learned model, you just use, for example, lane-based lane-based prediction models, then it's actually slightly worse than deep learned models. So that gives us kind of confidence that, yeah, indeed, deep learned models are useful and helpful. But then interestingly, if we don't use policy planning, if you use the traditional one, actually deep learned models perform very similarly to the analytical baseline. And third thing is ego conditioning not only improves the precision, but also improves closed-loop performance. So it's a good thing to have. And then one interesting thing is that a more precise prediction model doesn't really necessarily lead to better closed-loop performance. So for example, the agent former is more precise in terms of AD and FD, but it gives worse closed-loop performance comparing to, for example, the simple rasterized model. And finally, temporal consistency is very important. This has been our hypothesis for a long time, in the sense that if you train a prediction model that requires repetitive sampling, and a prime example is, for example, you're using a CVAE with Gaussian latent, then you have to sample that Gaussian latent all the time. That's actually a disaster. So you can see this is showing an agent former. So the baseline agent former uses a discrete latent space, and this one we changed to a Gaussian. Actually, funny enough, in their original paper they use a Gaussian latent, and then we found that this is actually really bad for planning, because that means your prediction is like kind of jittering a lot in subsequent frames, and that's a very bad thing for planning to handle. Okay, so to conclude, today I mainly talk about policy planning and as a potential improvement over traditional trajectory planning to consume the result of a prediction model. And what we found in our experiment is that sophisticated prediction is not really needed for most scenarios. You just have to follow the lane. But when they are needed, right, deep learned model still shows benefit comparing to analytical baselines, but this benefit is more more pronounced when you're using policy planning. A more precise model doesn't really lead to better planning, but then a temporary inconsistent one definitely doesn't give you good performance. E-conditioning is great. It enhances prediction accuracy and also the planning performance, but then it's very expensive. That was found to be the major computation bottleneck of our approach. And ongoing, we're kind of doing gradient-based policy planning with deep learning models, so we want to actually close the gap. We're designing prediction models tailored for policy planning, so get rid of a lot of the information that may not be needed. And also we're considering this kind of dynamic and continuous branching, so that you're not branching at a fixed schedule. And that's it. Thank you for your attention, and happy to take questions.
This pretty cool presentation. Thank you very much. But I'm afraid we're heavily behind the schedule, so I'm afraid we don't have the time to for the question and answer. So if you any of you have any questions, so please feel free to send an email to Dr. Yu Xiaochen, and so we may need to move to our next speaker. And yeah, our next speaker is gonna present in person, and Olga Sebinga is a PhD candidate at Delft University of Technology, working in the field of human-robot interaction. With a background in mechanical engineering, he has always been fascinated by the combination of mechanical, electrical, and software engineering, but throwing humans in the mix of what makes things really interesting. Many robots can behave safe and optimal in their own perfect isolated world. But to make modern robots, such as automated vehicles, function in the real world, they must be able to interact with humans in safe and natural manner. This is where his current work focuses on. Understanding human driving behavior and describing it in a mathematical way such that automated vehicles can make decisions based on their understanding of humans. So I will make you as a co-host. And let's welcome our next speaker.
Yes, great. Thank you very much. Maybe you can mute your audio. Yes, thanks. Awesome. Thanks for that introduction. So let's see if my presenter works. Yes, it works. So today I will tell you about how risk perception and communication can be used to model traffic interactions by human drivers. So most of what I'm going to tell you today is based on my very, very recent paper that was published, I think, 2 weeks ago. It was in archive for a bit longer, but it's this work that I did together with my supervisors, Arkady Skolnikov and David Abink. So if you're interested in this, then you can look it up there. And basically, my interest is in scenarios like these. So this is a video that I found on YouTube, and it's taken recently in a situation somewhere near New York. And it shows how human drivers can actually surprisingly well handle this very, very strange situation where there are no lines on the road and there is part of the road blocked by cones. And still they manage to, well, handle this without colliding. And this is what I'm fascinated in. And I'm trying to model these kind of situations to see how humans solve it so that we can learn from human behavior and in the end make better AVs. That's the idea behind it. And there are a lot of aspects here that have been mentioned before today. So there is some communication going on and there is some nudging going on here and there. And a lot of uncertainty, of course. So that's what I wanted to understand. So back when I started my PhD, I started off with this scenario. So I started from a scenario perspective and tried to figure out what I needed to do to effectively model this. And if we look at a merging scenario with 2 human drivers, there are a couple of aspects that are important. First of all, it's something that plays out over this distance or in time or in space. So it's some continuous interaction that's going on. It's not just one single decision moment. And during this continuous interactions, these cars, well, they show accelerations and velocities. So somehow they have continuous input signals. And it's, as I said, not just one single decision moment. And this causes a dynamic negotiation. But also there are multiple ways how it can play out. So this blue vehicle might decide to merge at the very beginning of the merging lane, but it could also merge at the very end. So there are many possible outcomes. It's not just I yield or I go first. So as I said, my approach to understanding how humans do this is to make a model. So I started to look at these aspects of this merging scenario and how they are reflected in current approaches. So I started off with traditional driver modeling. And I looked at a lot of traditional driver modeling approaches. And basically this car following example shows something that they, well, mainly do. So the main strategy that they take is in a situation like car following, you look at the vehicle you're interested in. So in this case, that would be this orange vehicle. Then you define some metric, for example, a gap in time or distance. And once you have this metric, you measure it, you gather some empirical data. And with this empirical data, you create a theoretical model that you can then fit on the data again. So that goes both ways. And for traditional approach or situations like car following, this works very well. But there's one underlying assumption that's not immediately clear from this schematic. And that's that in this scenario, the blue vehicle influences the behavior of the orange one, but it doesn't work the other way around. And we called this the one-way interaction assumption. And this works for car following and scenarios like that. But if we're going to look at merging, this won't work anymore. So if we put up the list or pull up the list that we just saw, are these things represented in this model? Well, we have continuous input signals. We don't have a single decision moment, but there's no dynamic negotiation going on because of this one-way interaction, because the blue vehicle cannot change its behavior. So there's no continuous interaction going on in a model like this. And also there are not many possible outcomes on a higher level because it's just car following all the time. So most traditional driver modelings make this one-way interaction assumption. And that's why I looked further than the traditional driver models. And then you end up with the game theory-based models. And they do something different because they basically model the thing as an interaction between two drivers. So blue, in this case, has a model of what orange is going to do and then decides I'll go first. Orange has a model of what blue is going to do, and based on that decides I'll go second. And this is a simplification, but most of the traditional driver models based on game theory work this way. So here we do have mutual interaction or reciprocal interaction, but there are some other problems because we do not have continuous input signals. We can have some dynamic negotiation, but that requires us to repeat this game over and over again. And the same holds for the decision moment. So in the traditional sense, there's one shot, one decision moment, but in the some other approaches, this is repeated. So that can be implemented, but in essence, it's not there. So continuous interaction is difficult for most traditional game theory-based models. And also the many possible outcomes are difficult because game theory scales very poorly with these extra outcomes because you get very high dimensional spaces that you have to search over for possible solutions. And there are two other things. Game theory assumes that people always rationally maximize some sort of a utility function. And that assumes that there's no communication. And these two things, well, we actually know that they are not what humans actually drive like. So to dive into them a bit deeper, let's start with this rationality assumption. Let's see. So we know that humans are not rational, even in very simple games, or at least not in the sense that traditional game theorists would call rationality. We also know that in driving, they don't rationally continuously optimize their velocity. So if we look at this driving scenario, then there is something that could be applied to it. And that is what Simon argued back in the 50s already. And that's the concept of bounded rationality. And Simon actually said, well, humans do not have the time of the mental capacity to continuously optimize their coming trajectory. So basically, they can partially optimize, or they might sometimes optimize, but not all the time. And therefore, he introduced the concept of satisficing, and that is basically using solutions that suffice and that satisfy. So basically, solutions that are good enough. So, for example, for the orange vehicle in this example, instead of determining, okay, in 5 seconds I want to be at this specific position, it determines, okay, in 5 seconds I want to be roughly there. So it's more a rough solution that is good enough. And this is a concept that I will use later on. And this has been advocated for driver models earlier, so it's in car following. So the takeaway message here is that we should prefer bounded rationality over full rationality if we want to model human driving behavior. And the second assumption of game theory was that there's no communication present, but actually, so we do know that communication happens in driving, and it can be either implicit or explicit, where implicit is basically just vehicle motions and explicit can be indicator lights, for example. And we do know that communication plays an important role in traffic. And beyond that, we also know that it is used in interaction models in other scenarios than traffic, for example, for bottle grasping tasks. And it can also be used to effectively control cobots. So those are like driving platforms that maneuver around walking humans. And finally, there's an interesting aspect here in communication, and that's the fact that for game theory, basically the target is a competition, whereas here in driving, we are talking about cooperation quite a lot because there's one main goal, and that's not to collide. And then communication can actually help, because if you tell others what you're going to do, the chance for a collision is way lower. Whereas in a competition, such as in chess, it doesn't make sense to tell your opponent what you're going to do, because then you will lose. So this communication can also play a very important role. So in summary, we have traditional driver models that consider one-way interactions mostly, game theory that says reciprocal interactions, but both are not sufficient to tackle this merging scenario at this point. And for game theory, that's mostly because of the rationality and a no communication example. So the idea was to use what's there and to start with a new model. And one thing of the traditional driver models that I haven't mentioned yet is that there are some underlying factors that are modeled in individual drivers that can be used in models of interaction as well. So this is the work done by Sarvesh Golokar, which was another PhD student at my department. It was published back in 2020 in Nature Communications. And he basically created one model that could tackle seven different driving scenarios. So you can see them all here. And this one model was based on the perception of risk. So what he basically said, or what he used, the concept that human drivers look at the consequence of events that would occur in the near area. So for example, hitting a tree is very bad, so that has a very high cost. Going off road is a little less bad, so that has a lower cost, and hitting another car is also bad, so that also has a higher cost. And if you multiply that by the basically the probability that you will end up there, so it's the direction you're heading in and the velocity you have play a role here. If you multiply those two, you basically get a quantified risk field. So you basically get a risk field. Okay, I know hitting a tree is very bad, and I know I'm heading for a tree. So those two multiplied means that I should do something. And he modeled drivers by trying to keep this risk under a certain threshold. And that could explain 7 different scenarios, but all individual driver scenarios, so no interactions. So that led me to come up with a new model, basically. And the focus of this new model was to describe the joint system, just as game theory does, include communication, and use bounded rationality. So with these 3 points, I started off. So as I said, we focused on the joint system, so on the complete interaction, instead of trying to model one driver, because then we had to make the one-way interaction assumption. And with this joint system, we started off with the idea that all drivers have a plan, and this plan is deterministic. So all drivers know where they will be going, or at least what they want to do in the near future. And they communicate this plan to the other driver, because by communicating, they can lower the risk for a collision. Then the blue driver in this case, well, he constructs a belief about what orange is going to do. And this belief is probabilistic. So he doesn't know exactly what orange is going to do, but there's a probabilistic belief. And this is close to the theory of mind that we discussed earlier today. And this works the same way the other way around, so it's symmetrical. And then this belief and this plan are coupled by the risk perception that we just saw in the other one driver models. So basically, if you know where you will be or where you plan to be in a couple of seconds from now, and you have some idea of where the other person is going to be at that same point in time, then you can estimate the risk of a collision. And we assume that drivers act to keep this risk under a certain threshold. So they do not continuously optimize their plan, but once the risk gets too high, they update their plan and therefore make sure that they can, drive safely. And we called this a communication-enabled interaction model because, as far as we know, it's one of the first model of interactions that explicitly includes communication. So this framework that we set up basically consists of a number of components. So the most important one are a plan, and that plan just needs to be any trajectory planner that can take the constraint in the form of a risk. So if we replan, we want to lower the risk. This belief can be any probabilistic belief, but it has to be updated with communication. And this communication function just needs to be some mapping from observations to belief updates. And this sounds very abstract and vague, and that's basically done on purpose, because with this general framework, we can select different methods from literature, and we can use them to our benefit. So for this plan, for example, we can use the concept of model predictive control, on which a lot of literature exists. For the belief, we can use Gaussian distributions with Bayesian updates. And for the communication, I just used a constant velocity model, and I observed the velocities. So by using this framework, we can leverage what's there in literature already. And to test it, I targeted this very simplified merging scenario. So instead of using this lane, which was the purpose of the model, so we will hopefully end up with it in the end. But for now, we only use a single merge point, so the drivers cannot steer, they can only accelerate or decelerate, but still they have a continuous interaction going on with a continuous negotiation to make sure that they do not hit each other at the merge point or afterwards. So how does this model implementation work? Well, I set up this slide to talk you through it, basically. So we're going to look at this interaction from the perspective of the blue vehicle. First, this blue vehicle makes some sort of a plan to initialize. This plan just has the form of a set of waypoints over time. So this is the plan for the near future. Then it tries to communicate this plan to orange. And in this case, it just used the implicit communication. So it starts moving. And by moving, it communicates to orange, okay, I'm going towards the merge point. Now, orange also does something, but for now we'll skip it because we're looking from the blue perspective. That makes it easier. So orange has done some things internally and also starts to move. And it might be that the orange car decides to move a little bit faster than the blue car in this case. So the blue driver here observes the position and the velocity of the orange vehicle. And based on this position and velocity, it constructs a belief. And this belief is just like the plan, a set of waypoints over time. Only here, every waypoint is not a deterministic point, but it's a Gaussian distribution over positions for that specific point in time. And if you combine these, so the Gaussian distribution and a plan point, for example, for this point in time, you know where you are going to be, you believe that the other person is going to be somewhere in that area, and then you can calculate the probability of a collision. And if this probability gets too high, you update your plan. And in this case, you could, for example, move this blue point further away a little bit. So if you move it up, then the overlap between the Gaussian and the point will be lower, thus the probability will be lower. So then the big question, of course, is, does it work? And I tested it in some simple simulation environments, and I tested it in a number of scenarios, but I talked through 3 of them here just to give you an idea of what happens. So in the first scenario, we set the vehicles up to reach the merge point with a very, very small projected distance gap. So they would not collide, but there would be a very small gap. If you would do this with fully rational humans, and you do not explicitly incorporate some gap keeping behavior in the reward function, they would, of course, keep this gap because no collision, so that's fine. So what happened here? Well, first of all, the positions. So this shows us basically the gray lines that you can see here connect the dots, which are positions at equal timestamps. So this shows us that the blue vehicle goes first. Well, we kind of expected that from the scenario already. But if we look at the velocities, we see something interesting, because you can see here that the orange vehicle actually kept its initial and desired velocity, but the blue vehicle started to decelerate or accelerate at a certain point in time. So apparently this small distance gap wasn't good enough for the blue vehicle. So with the small distance gap, the possibility of the orange vehicle accelerating and causing a collision was too high. So the risk was too high. So it started to accelerate to increase the gap. So actually the model here showed that the safety margin was too small and increased the safety margin to a bigger distance gap. And this is something that we see as very plausible human behavior, because a distance gap of, well, 20 centimeters was it in this case, is just way too small. So then we can look at the acceleration profiles that are not that interesting, but you can see the same thing happening in the perceived risk. So in this case, you see the dashed line, which is the upper risk threshold. There's also a lower one. If you want to know more about that, I invite you to read the paper, but look at the upper one now. It's the same for both vehicles in this specific case. And you can see that the risk for the blue vehicle actually reached the risk threshold because it was moving a little bit faster and was approaching the merge point earlier. And at the point where it reached the threshold, it replanned, so it started accelerating, and that corresponds to this little star here that shows you that it replanned. And then once the risk was mitigated and the interaction was over, it replanned again, and it started to slow down to get back to its desired velocity. So we also put them in another scenario where they were on a collision course, but where we tested different risk thresholds. So in this case, the right driver has a higher risk threshold, which basically say it accepts more risk, so it will take actions later, and the left driver has a lower risk threshold, which means that it will try to mitigate the risk early on. So again, we have the positions. So the orange driver went first in this case, and here we can see that both vehicles started to slow down because they both thought, okay, the risk is too high. But at a certain point in time, actually orange here realized that, okay, blue is also decelerating, so blue is solving the problem. So if I'm also decelerating, we will still end up in a collision. So I can accelerate now and make sure that I reach the merge point first. So there is some interaction going on here during the approach for the merge point. And they're updating their plans at points in time where they think that they can better change their behavior. And this shows also the flip in behavior, where it initially thought, okay, let's slow down and go second. It then changed its high-level behavior for another outcome and eventually went first anyway. And that's also reflected in the risk thresholds. So there's one more scenario that I wanted to show you. And this is one that we observed as emergent behavior. So we saw that these gaps were not only increased at the merge point, but also afterwards. So after the merge point, there was a small car following section, and we saw that the vehicles also kept a gap there. So we started examining this. We put two vehicles in on a straight road, no merge point or nothing. And we gave the following vehicle, so the blue one in this case, a higher desired velocity than the leading vehicle, so than the orange vehicle. So blue wants to drive faster than orange. And what we see here, again, the same plot, but the most important thing is the gap here added at the bottom. We see that that the gap reaches some steady state and that it's kept there. So instead of tailgating and driving bumper to bumper, these vehicles actually kept the gap and they, well, adjusted their velocities to some steady state behavior. And we tested this for multiple velocities. So we started to increase the velocity. And actually we saw a pattern here where if you increase the velocity of the vehicles, the gap in meters also increases. And this is something that we know also happens in human highway driving behavior. So with higher gaps or with higher velocities, we keep higher distance gaps. And remember that there's no gap, so there's no reward for a gap, not a time gap, not a distance gap, or nothing in this whole model. It only says, okay, if you are driving, there is some possibility that you might accelerate or decelerate. And because I want to keep my risk under control, I keep my distance, because if you suddenly slam the brakes, then there might be a possibility for a collision. So we feel that with this, we found actually an underlying reason for that explains human driving behavior, by keeping a probabilistic belief and keeping your risk under control. So what did we conclude based on this study? Well, and these are the conclusions from the paper, basically that the model avoids collisions and that the interactions that we saw were plausible, that the risk thresholds can cause more aggressive or more conservative behaviors, and also that this gap keeping behavior emerges. And all in all, we think that therefore this model is a promising approach for modeling these interactions, and hopefully we can learn a lot from them, so that in the end we might be able to understand what's going on here. And well, if we understand that, we can go on to the more complicated scenarios like this. Thanks for listening. If you want to keep in touch, you can reach me there. And feel free to ask your questions here or through any of these. Thanks.
Thank you so much. And any questions from the audience or online?
I have a question. So in one of the scenes that when the cars are coming together, and have a different risk threshold, they both decide to slow down. Did you do any simulations for that process?
Really back and forth is the time frame is just too short to actually get that behavior. So we did see this, and I'm thinking if we saw more than this, but I don't think so. Because actually what we're talking about here is this plays out in about 10 seconds, and then it's done. And we did put human drivers in the same scenario, and there we also saw this kind of behavior where they started out with the same thing and then changed their behaviors. But we didn't really see the back and forth thing going on. What we did see in human data, though, was that they sometimes towards the end of the experiment, maybe they weren't paying attention or something else was happening, but then they were on a collision course again. So they midgetated the collision course. And then towards the end, maybe the following driver started to accelerate a little bit, and then they came into a second conflict, basically. But then they also solved that most of the times. So we did see multiple conflicts in human behavior sometimes, but not really the negotiation going back and forth over time, because for that the time frame is just too short. At least that's what I expect. Yes, go ahead.
So this is the two-way interaction.
Yes.
But in the video, it's three. It would be three because there's a lead vehicle, trailing vehicle, and transition.
Yes.
Does this also support you're trying to make it heavy?
Yes, so one of the interesting things of the framework, let me see where, somewhere around, just for, trying to find it. Yes, there we go. So one of the reasons I set it up this way is basically that this big dashed line in the middle shows that these two vehicles are only linked by the communication. And this communication are just observable signals. So it's lights and it's vehicle movements and things like that. So in principle, it should be easy enough to just replicate the drivers and extend it to multi-driver frameworks. That's the theory. We haven't tested it though yet, but this is one of the things that I'd like to investigate. But in theory, the communication is broadcast, so you can keep beliefs of all the other drivers. And then you get into the whole, well, theory of mind discussion, of course, into how capable are humans of keeping predictions of multiple other users. So I think there has been some work done on that where it shows that it's at least limited, so that humans interact with a couple of others, but not with all the traffic participants there. But that's certainly something that we need to figure out then. Yes.
I'm curious to know whether you think that latency is or communication is something to consider in this kind of a setup, like
That's a very interesting question. Yeah, honestly, I haven't really thought about that yet. So the first thing that pops up for me is where that would happen then. So if there's some time aspect that could be internally on the human side, of course, it could be in the observations. So that's one of the things here. We basically assume that humans can always see the other vehicle and that always observe the other's position and velocity. And I've done some eye tracking studies with some master students in a very similar scenario, and there we can already see that human drivers don't always look at the other vehicle. They also look at going ahead, seeing if they keep straight, and some other tests. So I would be interested in figuring out mainly the source then of and if we can model that. So yeah, but I haven't looked at it yet. No. Yes.
Do you think we can adapt this framework to like other scenarios, for example, like unsignalized traffic intersections, or is it more specific to lane?
So at this point, it's all very, very straightforward. So the path planning, it just keeps in mind desired velocity and minimizing absolute accelerations for comfort. That's the only two things. This belief space is just based on some maximum acceleration. So you just believe, okay, the other vehicle can maximally accelerate with this value. So then the probability of it ending up somewhere in the near future is this. And then, of course, the constant velocity model included. So I think for the most important difficulty then would be to actually extend it to multiple dimensions, because here there's just no steering involved. But once you have that, I think it's general enough to at least apply it and see what happens. And then I think, as I said, it's set up in such a way that you can pick elements from literature to improve it. So especially for the belief thing, I think a lot of the prediction models that are going on out there would be very interesting to see how they would work in a belief aspect of this model. And they can still model the risk thresholds and the planning in other ways. So yeah, I see a lot of potential at least. Yes. Yes.
For the inverse communication path and theory of mind, what would you see advantage compared to just simply extended, or what's the best benefit for scenarios?
Yeah, so I think so the goal here is to model human behavior, right? And that's first and foremost the thing. So this thing is not meant as a controller or as some control approach or anything, because it also shows collisions, for example. So that's something that we might want to predict, but not control. And if you look at it that way, I think that the differences between implicit and explicit communication in human behavior have been studied quite extensively. And it has been shown that implicit communication plays a very big role. And explicit communication also plays a big role, but only in very specific scenarios. So this turn indicator, for example, is a very specific indication for a lane change or for turning left or right. But in many other scenarios, we just lack these implicit or explicit communication signals. So you can wave or you can keep eye contact. And we know that people do that in urban scenarios with very low velocities. But for these highway scenarios, that's at least very unlikely. But also we know that for a lot of scenarios, the implicit communication plays a very, very big role, and maybe even more important than explicit communication.
Well, that's great. Thanks, Mr. Elker again.
Yeah, so we move on to the next keynote talk, and it's my pleasure to introduce Professor Catherine Campbell from the University of Illinois, Urbana-Champaign. Catherine Campbell is currently an assistant professor and running faculty fellow at the University of Illinois at Urbana-Champaign in the Department of Electrical and Computer Engineering. Prior to joining the university, she received a bachelor's with honors from Arizona State University in 2012. And a master's degree and PhD from UC Berkeley in 2015 and 2019, respectively. And afterwards was a postdoc in the Stanford Intelligent Systems Laboratory. Kathy now runs the Human-Centered Autonomy Lab, which aims to design safe autonomous systems and robots that can safely interact with people out in the real world. She's a recent recipient of the NSF Career Award and IEEE RAS Early Academic Career Award. Please join me in welcome Professor Cathy Campbell.
Thank you for that introduction. So hopefully everyone can hear me okay?
Yes.
Awesome. Okay, great. Well, I'm super excited to be here and chat with you all today. It's been some really, really cool talks. A lot of what my group does is we think about how we can create interactive and safe autonomous systems. So thinking about how humans and autonomous systems should interact and how we can model these behaviors are sort of a key part of what we do. So I'm super excited to hear about all the cool stuff that's been going on in this area. So today I'm going to be presenting a line of work in my lab that we call people as sensors. And this is an approach that we've coined to kind of capture how we can start leveraging and using some of these human models to help intelligent vehicles or autonomous systems start using this knowledge and insight from human modeling to infer more about the environment than they normally might have. So to jump right in, normally when we start thinking about human modeling, this can mean a lot of different things depending on what piece you want to work on. This can be game theoretic models like we learned about in the last talk. This can be predictive models like there was a few lectures or talks ago. We can think of things like driver traits. So really thinking about sort of more higher level abstractions, like if someone is passive or aggressive. We can think about driver modeling as sort of internal behavior, so looking inside the vehicle. And all of these different things sort of have different roles to play, but they all can provide us some information about the decision-making and processes of the human. And what we're going to be talking about today is how we can start making use of this for inference. And one of the motivating examples that we're going to think about is vehicle pedestrian modeling. So let's do a quick look at that. So if we were to put together an autonomous vehicle together, we'd have a bunch of different modules together, and we'd have a bunch in there that has to do with basically this prediction element or trying to come up with this human model so we can incorporate this in. So we can have something like detecting, say, a pedestrian or maybe some other agent. We can predict their goals and predict their underlying trajectory that they're going to follow. And then we can have something like safe interaction here. So again, we can have something like use these models to predict where this person is going to go. This could be another vehicle. If we wanted to understand sort of different levels of interaction, we could use these models to understand how this interaction should happen. But there's lots of different things that we could use to employ here. And this is sort of the traditional view of what people think about when they start thinking about predicting human behavior. They want to sort of think about these close interactions and how we can basically look at these usually two agents interacting. But as I mentioned, what we want to start doing is thinking about this idea of trying to make use of this for inference. So now what we want to start doing is, instead of just start thinking, okay, I can detect this person or this vehicle, this agent, where will it go? I want to start thinking about, of the agents I can detect, what is causing their behavior, given that I have some model, and how can I start using my observations of these agents to learn more about what we think the human is going to do, or what these agents are going to do, and how it reflects the environment. So as a little example, this is sort of something that people do all the time. So this is a quick video. I'm going to pause it real quick. I can't pause it. So we'll go back and pause this real quick. So this is a video. So this car is approaching a stoplight. What we'll see here is you can see that there is a green light. So this car should be free to go. But we'll see that there are some sort of interesting things that happen here. The first interesting that happens is this car that is in the middle of the intersection starts to slow down, even though it does have this green light, and then a pedestrian is going to pop out. So the interesting thing that happens here is the vehicle that we are watching via the dash cam actually starts slowing down before the pedestrian pops out. So we see that there is something interesting happening with this truck. We observe this behavior and we make an inference that something is likely going to happen, and we are able to stop in time for this pedestrian. So basically, what we see in the real world is people are not just looking for, I see a pedestrian, I'm going to stop, but they observe the behaviors that are going on around them, and they start basically inferring or being a little bit more proactive about what they cannot see. So humans are able to really pretty intuitively capture behaviors or intelligently interact with occlusions. So even if we can't detect these agents, we can still do some intelligent things. And now I will say that this is not always the case. There are plenty of examples where there are many close calls and people do not infer things correctly, but by and large, people are very, very good at this. Let's sort of think about this more formally. So as a simple example, we're going to think about this case where we have multiple agents. In this scenario or motivating scenario, we will have a pedestrian, an occluding vehicle, and then the agent that we are interested in making the inference for. And then we want to be able to handle this occlusion. So again, if we wanted to sort of always assume the worst case, or always assume that there was going to be something in regions that we can't see, this would be sort of the safest. We can always assume worst case, but this would be overly cautious, and it can actually potentially lead to more dangerous behavior. The alternative is you can assume you only what you can see is around you, and in that case we have very dangerous behavior. So we have these sort of situations where we do need to be able to reason about occlusions intelligently. This is something that, again, people do all the time. So people are pretty good about reasoning about spatial uncertainty, even if it is something just like taking their time to gather more information. We argue, and this is something that many people have said, I'm sure throughout the day, but we want our autonomous vehicles to have similar intuition and sort of be able to interact naturally in these human environments. So specifically in this case, we want to make sure that these intelligent vehicles can have similar occlusion inference capabilities. So we're specifically going to look at that. So the question we want to start posing is, if we observe different agent behaviors, can we start making inferences about other agents in the environment or other obstacles potentially? In this case, let's just say, can we watch this vehicle, this sort of green box, and make an inference about whether or not there is a pedestrian present? So in this case, we can keep it very simple. If a car is slowing down, we can start thinking about why they're slowing down, and it's likely because there is a pedestrian there. So can we make improved inferences about the state of the environment by observing these other agent behaviors? So this is our problem statement. This is what we want to build up to. And as a sort of quick aside, we are going to start looking at different representations that we can start reasoning about occlusion. So I'm sure everyone knows perception is basically how we take all this raw sensor data and make sense of it. So the most common way we start thinking about representing perception is in a very semantic manner. So you can see in this image on the right here, we typically annotate or do things like object recognition. So we have things very sort of clearly laid out. While this is very intuitive, and this is sort of how we as people reason about things, the sort of classic sort of object-centric view typically is more aligned for the sort of the view of if you see it, it is there. And it doesn't really help us reason about these spatial uncertainties or spatial occlusions. So what we're going to do is we're going to take a slightly different take. We're not going to reason sort of in this semantic way. We're going to actually look at occupancy grids. So this, we're going to lose some of the insight that we get from having things very precise, but we gain more insight into the likelihood of generic obstacles, perhaps agents, perhaps not being present. Again, what's nice about this is we can explicitly reason about the presence or about occlusion. So we can explicitly say if we do or do not receive a sensor measurement from a particular region, and we know explicitly where unknown regions are. So in this little GIF on the right here is our occupancy grid representation that corresponds to this view, where this in the center here is our car. So we have the free space, which is indicated in blue. We have known occupied space, which is the red, and then in between we have this uncertainty. So this light green is this sort of uncertain view where we're not getting sensor measurements or we're not sure what's there. So again, what's nice about taking this view is it allows us to reason a little bit more explicitly about what we know and what we don't know, which is really nice when we're trying to think about being aware or more sensitive to things like occlusions. Again, we do lose some information, but we also gain some other insights in some other ways. And again, there's one other thing that's really nice about this is it's a little bit more similar to an image. So it also allows us to make use of a lot of the image processing tools and computer vision techniques to start reasoning about this image a little bit more explicitly. All right. Okay, so now let's start looking at a very simple approach. We're going to, again, look back at that case where we have these just 3 agents that we're looking at here. So we're going to build on this occupancy grid approach where we assume we have this collection of cells. Again, they're going from 0 to 1, where it's more likely that they are occupied here. So we can define our occupancy grid, and it's going to look something like this in this case, where if we have the ground truth, we have the cells which our agents are in, and these are occupied. But due to sensor limitations, we sort of have this triangle view where we have all this region where we have our unknowns. And this is sort of where we are dealing with occlusions here. So when we start thinking about how we can take into account this mapping situation, we basically lean into the sensor fusion approach. We start thinking about how we can take this idea, and instead of just using sensor data to update our map, we want to start making use of driver models. So again, we call this people as sensors, where we have our driver model here. So we have the probability of some action given some map. So the only difference between a generic model would be we often don't work on maps directly, but we have some sort of input that we are looking on, either past information, we want to say what they're going to do next, or we say, given that there is something in front of them, what are they going to do? So this is basically just updating or changing this update rule to account for a driver model, again, which is typically what we would get anyways. So if we take all this, we incorporate this together, we can start looking at how we can update and improve this map. So in this case, here we have our standard map. So this is where we basically aren't doing any intelligent updating. And this is where we are starting to look at how we can take observations of what's going on and start updating our map. So in this case, we see we're observing this blue car. It is at first speeding up. So we see that it has a sort of free zone in front of people. At some point, it will switch to slowing down, and we'll see the map change so we can infer that there is some sort of obstacle in front of it here. So we're here, it starts slowing down, and we see it switches. There is a slight delay, but we see it switches to saying that there is some sort of obstacle or something in front of this. So we can see how this kind of updates and can start giving us more insight to what's going on, again, just by observing what's around us. Now, this is sort of a simple example. Even the actions that I'm saying are very discrete, which isn't really practical. So what we want to do is we want to expand this to a more multi-agent view here. So in this case, we're starting to look at a lot of different agents. So in this case here, we have now 2 different observed agents and some occluded as well. We want to come up with this driver model, as I said, which is going to take this environment and head of each vehicle. And we want to basically map these observations to what is triggering them. So again, this is basically this driver model. We want to start reasoning about observations and the environment. We do this for all the vehicles, not just the one like we had before. We start taking into account these regions that we cannot see, because again, now we can explicitly reason about our occluded areas, and we can start thinking about how we can combine all this together into the ego vehicles map. So in the previous slide, we were doing a simple Bayesian update. When we start adding more vehicles and we have more conflicting information, we do look at slightly different approaches to sensor fusion. We've been using Dempster-Schaefer theory, which allows us to explicitly reason when we have conflicting information. But it's a similar update, again, where we're basically taking our models and using this as something like a probabilistic update to give us more insight to what the likelihood of an obstacle in each cell is. Okay, so the first thing that we need to do is basically need to come up with these driver models, which before we sort of swept it under the rug, we just sort of assumed we have it. So let's first talk about how we come up with this, this sensor model. So we're going to do this by using a CVAE, so a conditional variational auto encoder, encoder. So basically what this is going to do, this is going to help us learn this function that maps some observed trajectories. So these are the observations that we have of these different agents to these maps. Again, and these maps are basically these pieces of the environment. These are basically the things that are going to cause the behavior that we observe. So we're going to use these CVAEs as generative models. So they're going to encode these observations into our latent space. And then when we're doing this training, we're going to basically convert this or decode this into a reconstructed output. So we want to reconstruct this map from this here. So here we have our encoder. So this encoder is going to represent this categorical prior. So this is our prior over our latent space. In this case, we have a discrete set of maps that we can build from. And really that's just to make it a little bit easier to learn. Then we are mapping this into our posterior Q, which again is these latent variables given our observations and our maps here. So these decoders are then going to take these latent variables, convert this into our reconstructed map. Again, that's just in front of the driver here. So again, we have our observations, we have our ground truth map. We're going to take this all into our autoencoder. It maps this to this latent variable, and we can decode this into our map here. So basically what we're going to do or here though, is at test time, we are just going to take this trajectory. So we have this observed trajectory, we pass this into our decoder and we get our estimated output here. So again, this is basically just our driver model that we can then start sort of piecing into that map from before. So to learn all this, we need a lot of data. And for this, we use the interaction data set. So we took one of the interesting intersections here. We basically converted everything in this top-down view to occupancy grids. So we can sort of get full information about all the occluded space here. And started basically building up our driver model here. And so you can see here, these are just some examples of our learned sensor models that we then can pass into our updates. So let's look at a few examples here. So here's a case where we have a vehicle that is slowing down. So this is our trajectory of basically we're slowing down here. And in this case, we can look at different likely inputs that cause this. So intuitively, it is most likely that there's some obstacle in front of the agent that causes this behavior, but maybe it's just keeping up with traffic. So there is a chance that it's actually free here. And one thing that's really nice about this CVAE approach is you can be multimodal. So you can take into account that there are multiple things that can cause similar behaviors. So we can query our model, we can get these multiple modes, and we can see which one is actually true or what actually happened. Similarly here, this is a case where we have a constant velocity vehicle where our two most likely modes are either you're following traffic. So this case is where it's becomes a little bit ambiguous, where here we do have an obstacle, but everything is constantly moving, or we just have free space and the vehicle is moving. And we have these that are equal weight, which again sort of tells us a little bit more about the uncertainty and the sort of multimodal nature of human behavior. So sometimes it's hard to sort of tease out the cause, but given this model, we can at least come up with both examples here. So here's an example just sort of some of the driver models that we can get from here. So now what we need to do is start incorporating this into the ego agents map so we can start filling in all the occluded space. So here's a scenario where here we have our ego agent and we have lots of different agents that are surrounding this agent. And you can see this is causing a lot of different occlusions. So the one that is sort of most relevant here is this agent right here. So this is oncoming traffic that we cannot see directly, but might change how we behave as we are entering this, this intersection. So here we see this agent here being sort of our most informative vehicle at the moment. We observe that they are stopped, and now we want to update our map given this information. So we query our driver model. We see this vehicle is stopped. That means there's likely something in front of the agent. You can see we have this sort of darker spot. We can infer that there is some sort of obstacle here. In a similar setup, once this vehicle starts moving, now we can start inferring that there's likely free space in front of them. We can see that now we have this sort of free spot ahead. So say that could change how this vehicle is going to act. Say if they were going to turn or enter this, they now would be able to, and again, and do this in a little bit more of a proactive manner here. And I'll note we've sort of been focusing on this agent here, but we can note in these different examples, we are updating the map for all of these different agents. It might just not be as relevant since it's not immediately close to the agent, but we do get information about the full map given the agents that we are observing here. And same thing in this image here. So as I mentioned, one of the things that's sort of nice about this or using the CVAE as a modeling framework is we can get multimodal outputs. So we can start reasoning about the different sort of what ifs or what could be causing different behaviors. So again, in this example, we see this vehicle here is just sort of trudging along. There are two different options that they could be, or sort of two different things that could be causing this behavior. It could be free space, or it could be some traffic just ahead that is constantly moving. And we can see the likelihood that's associated with these different modes. So what's nice about having these different situations is we can combine these different possibilities together, and we can start basically changing how our map is assembled. So what's nice about this is we can start thinking about reasoning about worst case scenarios or best case scenarios, and we can start thinking about how to more explicitly take into account risks based on different things that could happen here. So how to pick the best mode or what actually is going to happen is challenging, but you can sort of query this, and you have some variance in sort of what you do and how you want to take that into account in your decision-making system. Okay. So really quick, so far what we've been doing is thinking about how we can do occlusion inference by looking at human behaviors. So we have this sensor model paradigm, and this gives us insight into what is causing these behaviors that we do observe. We have been using these occupancy grid maps, again, because this sort of lends themselves to a generic view of what's happening, and it does lend itself well to downstream tasks. So a lot of navigation and planning frameworks do work on these occupancy grid approaches anyways, so it's kind of nice that it's directly meaningful there, whereas some other approaches, it's not immediately obvious how you should take this into account into downstream tasks. Again, we've been using these sensor fusion methods, so we can fuse all of these estimates together. The key thing is we are basically taking these human models and using them as if they were sensors here. And we're able to do this with multiple different inputs from multiple different agents. The key modeling framework that we've been using is this conditional variational autoencoder, which is both nice because it can effectively capture human behavior and most importantly, can look at this multimodal aspects of it. And we did look at this on a real world data set that allowed us to basically look at really complicated settings here. We demonstrated real-time performance, which was very useful when we started looking at these real-world tests. So we did run this on a vehicle here, where we didn't use a real pedestrian, we had some fake pedestrians here, but we had some occluding vehicles, some sensor vehicles, and we're basically able to merge all this together so we can infer when pedestrians were going to pop up, as in that sort of initial scenario. So we can do things like infer this in safety critical scenarios, and this can tell us when to do things like be proactive about stopping and have more nicer behaviors, or sort of more well-reasoned in how we want to balance our risk in the presence of these occlusions. Just as sort of a quick aside, so for this, often how you reason about occlusions or how you take this into account for vehicles is a little bit strict. Often you just sort of decide how cautious you want to be or not. But this is also useful for mobile robots, or when you're in more pedestrian type environments. So this is useful when you have very limited field of view, which is typically not an issue for autonomous vehicles, but could be for some more pedestrian type mobility issues. So we can do a similar thing where, again, we want to start inferring presence of more occlusions. These cars, or the occlusions, don't have to be from cars, they can be from any object. And again, that's something that is nice about the occupancy grid framework, is it is agnostic as long as you have the data to train your human models. One final thing that we did also look into is how you can make use of this framework to improve learning policies. So we did also integrate this into a reinforcement learning framework, where now you're saying, if I observe this occlusions or these occupancy grids, can I reconstruct the full output here? So it's a slightly different view, but a similar idea, where we basically try to match these reconstructions here, so we can feed this into a policy and start making more informed decisions based on this. So I won't get into this because it's a slightly different setup, but we can take the same approach and start making inferences about what's going on around different agents, and still do effective navigation around people. And we can get this to work in real settings, but again, slightly different settings, so I won't go into it. But okay, so for today's insights, basically what we talked about was this idea of people as sensors, so we can push this idea of social inference. Again, we want to make use of all of these different human models and show how they can be used to improve environmental awareness beyond just the things that we are detecting immediately. So hopefully this can lead to more proactive decision making, and again, start building up similar intuition to what we as humans have naturally anyways. So with that, I would like to thank my students and my sponsors for actually doing all of this work. And thank you for listening. I'll happily take questions if there are any.
Yeah. Thank you very much for the awesome presentation. Any question, please? Online audience and person, feel free to ask a question. Okay, I have a question while others are thinking of your questions. Yeah, so I wondering what the drawback is for considering semantic maps that will give you high-level information about the different agents in a traffic scene, and combining this with trajectories of other agents for the purpose for the downstream tasks that you have looked at. So what's the drawback of using this kind of approach instead of using an occupancy grid map with trajectories of the other agents? Yeah, because I feel like when you use like high-level semantic informations, you are able to like provide explanations, clear, intelligible explanations for whatever decision the able vehicle or whatever vehicle in consideration has made. So are there any drawbacks for using higher semantic information plus trajectories rather than occupancy grid maps?
Yeah, that's a great question. And this certainly doesn't shouldn't be the only thing you should use. You definitely need some semantics and some things that that you know. And if you have the information, then you should, and you have a good way to use it, you definitely should. But the key thing about this work is it's dealing with things that are unknown and you haven't observed. So in this case, I don't know that there is a pedestrian that is behind this vehicle here. So there's no way for me to label it. Once I observe something like this agent slowing down, I can, and say I infer that there is some obstacle here. I might be able to do some sort of higher level or next level reasoning about what could possibly be there. But this is sort of meant to complement sort of the existing sort of standard or sort of more semantic based approaches where you can say on some level, it doesn't matter what is there. I just need to know how I should behave. So if there is something that is approaching the crosswalk, then I need to stop. So this isn't, again, meant to replace the more semantic reasoning, but it's meant to sort of allow us to reason about these unknown regions more explicitly where we don't have any information. There's some sort of similar work where you may want to do something that's more like tracking, where if you do see a pedestrian at some point and then it disappears and becomes occluded and then reappears, you can come up with it in between. But this is in this the situation where you might not have seen the agent ever. So it's just sort of reasoning at its sort of highest level there. Again, this is not meant to say we shouldn't have HD maps, we shouldn't have any semantic information. You definitely should have that. But there are regions where we can't have that information. We do have sensor limitations. We do have other issues. And this is meant to help with those sorts of situations.
Thank you very much. Yeah.
So just to play devil's advocate, let's say you're approaching this median, 2 lanes traveling, and the car is slowing down and stopping because there's a pedestrian on the exit of the right lane. Let's say the block car is turning right. With this method, hypothesize pedestrian is crossing our lane and cause the right car to slow down. And how would you distinguish, that this black car is slowing down for a right turn and with some of them exit?
So I couldn't quite hear you, but was the question how to distinguish between slowing down for like different reasons?
Let's say in this situation, instead of a pedestrian crossing across in front of a red car, the pedestrian is crossing, away from us, and the black car is turning right. So now the black car is slowing down for a pedestrian that's not crossing the road. And I think like the desired behavior for the red car would just to be not to slow down. How would you address kind of like not stopping for every vehicle on the right lane that's going slow?
Yeah, that's a great question. So I guess there's sort of two ways to answer this one. So first off, I guess anytime you look at these situations, I guess there's two things you have to realize. One, people are always communicating something, and it can be misleading. We just can't know everything. And we do have behaviors that are inherently multimodal. So people do have things that lead to the same thing. So I think, where's my example here? So in this example, this is sort of where we were talking about this is, we can see some behavior and there are many different likely causes of it. So for example, if we are going just at a constant speed, this is either because I'm following traffic or there's nothing in front of me. And there's also other examples that could be, but those are sort of two simple examples. And they both could be equally likely. And on some level we can't reason about, or it's very hard to reason about which one is more likely without some other context or some other sort of insights. So I guess on some level, human nature is inherently multimodal. So it's very hard to sort of deal with these things. But two, having a model that can actually generate these different options, so you can start reasoning about them. You can see what is more likely, or maybe even what is most impactful. So you can start reasoning about what could happen. So for example, in that crosswalk, if there's a chance that a pedestrian is coming out, yes, maybe you don't want to slow down every time, but you probably want to slow down most of the times, since that is a very high risk scenario where that pedestrian is a very vulnerable agent. So you can sort of think about how this can tie into your decision making depending on some more contextual cues and whatnot there. But But being able to reason about this multimodality is very important and very non-trivial there. Hopefully that answered your question.
Any other question? Okay.
This and thank you, Teddy, for your wonderful presentation. And I think that concludes our workshop today. And thank you all for coming and joining us. And thank you all of our speakers for your insightful opinions and wonderful presentations. So I think that's it for today. And if you have any further questions, please feel free to contact us and or any of our speakers. And thank you all. Bye.